on the first Thursday of each month on a topic drawn from the broad area of manufacturing, with a particular emphasis on Industry 4.0 and digital manufacturing. Welcome back to those who've participated before, and a special welcome to all new participants. Just one note before we start, that at the end of the session, there will be a link in the chat part of Zoom to take you to a poll in which we ask you to cast your votes for the best presentation of the day. Now, I just share my screen to give you advance notice of the next two sessions in August. On the 5th of August, we have a session on natural products and manufacturing, which, and on the 2nd of September, we will have a session on manufacturing and digital twins. Now, for both of these sessions, we already have some keynote speakers, but we would welcome suggestions or offers of other speakers. And if you have, or you know somebody who would be interested, please just drop an email to IMFS@ePileria. So thank you very much. And now we will have a short welcome from the President of the Polytechnic of Leiria.
Hi all, it's a great pleasure as President of the Polytechnic of Leiria to be here in this welcome session on the Virtual International Manufacturing Forum Series 2021. Of course, I want to greet all of you, but also I want to greet the chair of the conference, Professor Jeffrey Mitchell, as well all the integrated members of the Center of Rapid and Sustainable Product Development, the CDRSP, including, of course, the director, Professor Nuno Alves. This is a unique event. It's a huge opportunity to discuss the direct and digital manufacturing. In fact, during the whole the year of 2021, we will discuss every month one specific topic that we will share to all of you and with all of the world. In fact, we will start discussing in July the big print. In fact, for us, for the Polytechnic of Leiria, but also for sure for the CDRSP, this is a unique and pioneer event because it's a true open science strategy connected to open and free for all the participants. But I really hope that this outstanding series could be recorded and shared with all the world, not only through the higher education institutions and research units, but also with the companies that are connected with this topic, this outstanding topic of the direct digital manufacturing. Please enjoy all the event during this year of 2021. Thank you for all of you, for all the shares of the conference to participate and to disseminate research with impact to society. Thank you.
Good. Thank you, Rui. So now I pass to the chairs of this particular session, Olivier and Arthur.
Perhaps Olivier, good morning. Thank you, Geoffrey. So, yes, I'm Olivier Lau from Estia in France and Adimado, additive manufacturing platform based in France. I want to share effectively a very warm welcome to all the participants in this event. It's a great pleasure to be there. I want to thank IPLARIA for the invitation, Professor Mitchell and Artur Mateus. I think we are going to have a very interesting sessions all the day, and I hope you will enjoy these sessions. Artur, maybe you want to say some word.
Okay, thank you, Olivier. Thank you, Professor Mitchell, and thank you, the organization. As Olivier mentioned, this I think will be a great day to know more about updates in printing big. Also, I want to say that between Estia and the IPLARIA, we have not a long history of collaboration, but a short and good history of collaboration. I think since 5 years ago. So it's always a pleasure to organize this kind of things and others with Olivier and his team. Thank you very much, and perhaps we need to start the sessions.
Okay. So thank you, Artur, for your kind words. Yes, we have a very good relationship with IPLARIA. So maybe we have 5 minutes before the time, but maybe we can begin with the first session. So session 1, it's about wire metal printing. So we have it's a longer session, I think, of the day, because I think we have a lot of things to do. So the first keynote speaker, it's Professor Williams from Cranfield University. So I see that you are connected. So I will do a brief introduction before to give the floor to Professor Williams. So Professor Williams has been researching into material processing for manufacturing application for more than 30 years. Initially through an SME supplying laser system, then 20 years at the BAE system, and for the last 15 years at Cranfield University, where he is director of the Welding Engineering and Laser Processing Center. His main research activities are large-scale additive manufacture and laser processing. He is technical director and founder of WAAM 3D, a company set up to supply WAAM technology to industry. So please, Professor Williams,
thank you.
You can share your screen.
Yeah, thank you for the kind introduction.
You're welcome.
You need to enable me to do that. The host does. The screen sharing's been disabled.
Maybe Renato or...
Please can you turn on?
Okay, thanks.
Great.
Okay.
Yeah, great.
Okay, thanks. Welcome everybody. Thanks for coming along this morning. So I'm going to set the scene really about large-scale additive manufacturing, which is something that we've been looking into for many years at Cranfield. Just say a little bit about what the current status is and also what we're doing going forward. And I would like to acknowledge all my colleagues over the 15 years of our program, both from the WAAM program and currently from the new WAAM program. It's more than 30 people in our center and people elsewhere as well. So in terms of large-scale additive manufacture, what are the current approaches and challenges? Of course, large scale can mean two things. It can mean large area additive manufacture, or indeed massive parts. And our US colleagues refer to large area as big area. Maybe we need to follow suit. To do this, you can have several approaches. You can use a CNC system, single robot, a robot on a track, or multiple robots. And I'll give some examples of each of these different approaches. Say a little bit about how to build massive parts, which really requires high deposition rate processes. And then I will, second half of my talk will be about the future trends, what we're doing now, moving away primarily from commercial off-the-shelf energy sources to design ones. So this actually, this actually was one of the very early parts that we made, probably around about 2009 or 2010. It's a 3-meter long aluminium stiffener, which we built on a large CNC machine that was actually a friction stir welding machine. And you can see here, we were investigating whether or not there were any issues with it, whether it could be made straight and so on. And in fact, we were able to deposit it very successfully. And because it was also a milling machine, in effect, we were able to machine the part as well. So been around for a little while, but of course, most of our work is based on robots. And I guess you've got a big white square in front of that, have you?
Yes,
yes.
We have a big
a big white square. Yes. I'll just get rid of that.
Okay.
Okay, so there are 3 different approaches that you can take with the robotic systems. In the top left is a single robot, which typically gives you a deposition area of 2.5 by 2.5 by 1.5 meters. And here we're building an aluminium stiffened structure. On the right-hand side, you've got 2 robots doing the deposition, which enables us to increase the build area up to more than 3 meters. And of course, using 2 robots, we're able to increase the build rate also. And on the bottom left, you can see we put 1 robot onto a rail, and this is enabling us to build a 6-meter part. And that is the final part that was made using the single robot system. And I can see what's gone wrong there. Moving on to looking at the rear of a Euro Typhoon. Here we were looking at building one of these frames, structures that are inside the Typhoon. And we were successfully able to do that actually with a single robot. And you can see the part built here. And the goal here is to reduce the lead time from 100 weeks to 100 days. And we believe it's still the largest publicly known anyway 3D metal printed titanium part. There were many challenges associated with this, as you could imagine, principally to do with how to manage the distortion of this thin plated but large area structure. This is another example. This is looking at a 5-meter long construction beam made for Foster and Partners. And here we're using a single robot actually. And on a track, you can see clearly, of course, we're rotating the part. Most of our parts are double-sided. And you can see here the plasma deposition being used. And this silver grey box contains a number of sensors. It also provides local shielding to protect the environment around the deposition. So clearly one of the challenges when going to larger area parts is how to provide a shielded environment if the material needs that. It's not practical to have a huge room or enclosure so a local shielding solution is required. And here you can see the part after it's been manufactured being removed from the jig. This is an example of using 2 robots again. This is part of the LASIM project, which was an EU project with many partners. This system was built at Loxin in Spain and comprised of 2 deposition robots. And again, you can see the benefit of having the 2 robots with the multiple deposition. This was a relatively small part. This also included a robot for machining based around a triaxial configuration that made it particularly stiff. And you can see here it's being used for finish machining. So another example of an aluminium part where we do the deposition, and then the triaxial robot will then do the finish machining and the pocketing. As I mentioned, this was part of the LASIM project. One of the critical aspects of building large parts, of course, is how to manage distortion. Just as in welding, we have had many failures in our laboratory, as you can see here. And actually, when you're building this part, you think it's okay. And then when you take it out, it does this. And of course, this is a major fail. And these just have to go to the scrap bin afterwards. I don't really have time to go into how to control this distortion, but it requires a lot of background knowledge, particularly based around welding techniques. The basic principles of the distortion are the same. And if you apply these, you can eliminate the distortion completely. You can see on this bottom part, this is a double-sided part, which we often use to provide balancing stresses so that we don't get distortion. But in fact, when we took it out, we did get distortion, and this is due to buckling. So double-sided deposition doesn't really control that for you. But if you apply some techniques such as balancing the stresses, using an optimum build sequence, designing the tooling and jigging in a certain way that enables it not to be too highly restrained, then it's quite possible to build distortion-free components. And in fact, this one here is a single-sided component, and you can see all the green, yellow, and orange areas are where we have excess material. The only areas which we have missing material are the blue areas, and this is primarily just from some minor distortion in the substrate. So just as an example of how we go about building these massive parts using these techniques, this was a rib structure which we built for Airbus recently in titanium 6-4, which has a mass of 155 kilos. It has quite a few complex shapes and different wall widths that add to the complexity of the build. We built it using our standard plasma transferred arc process, and the challenge was to avoid distortion and or cracking. So how do we go about preparing for this? The first thing is to generate a preform, removing all the features such as holes and thin walls, which we cannot manage in the deposition process. And then we add extra material to the final part shape so that we always ensure that we have material in every area and we don't have any areas with missing material. In this case, we added 3 millimeters. We then apply finite element analysis to determine the residual stress development, to optimize the build sequence, to look at the design of the substrate and also the tooling, and where we should actually place the substrate within the part, because you can start in different areas of the component. Once we've done that, we then use the output from the modeling to determine the substrate dimensions and shape. We use what we call a conformal jig, and in this case, we also utilized preheating to avoid cracking. The part is then imported into the WAAM 3D WAAM software to generate the robot deposition path. And then finally, of course, we build the part. This is an example of the modeling that was used. This is using Abacus software with our own subroutines. And here we're looking at the residual stress development evaluated against different preheating temperatures, build strategy, tooling design, and substrate profile. So the picture on the left shows the stresses anywhere in excess of the yield stress is shown as yellow, as grey, sorry. And you can see that there are substantial areas where we would get cracking if we didn't do anything about it. And the picture on the right shows you the expected deformation. And here we're applying the preheating, and you can see, of course, a substantial reduction in the stresses and also a reduction in the expected distortion. If we combine this with the tooling design and the build sequence optimization, we can effectively eliminate the risk of cracking and also any outer plane distortion. This is a few pictures of the part being built. So this is the first layer, and you can see it looks very nice because it's the plasma process. This is again a double-sided part, but it's not symmetric. So this is layer 8, side A and B. What you can see on the right-hand side as well is the preheating mats that we used, which were clamped to the substrate. Of course, using preheating does impact quite severely on the build duration, build time. And this is layer 32, side A and B. And then this is the final part. We were building this at roughly 7 kilos a day, but that was primarily controlled by the size of the spools that we were able to utilize. If we were able to utilize larger spools, then we could probably have built this part in around about 9 days. But we weren't, of course, trying to maximize the productivity here. We were trying to build the part successfully. So as I mentioned, if you want to build massive parts, and indeed that is quite a massive part, you need to build more quickly, otherwise it'll take too long. In fact, it's been around quite a long time building quickly, and indeed 3D printing using wire-based DED, as it's called, or in other fields is called weld metal buildup. This is an example that I picked from 1983, where Kussmaul used what they called shape welding to manufacture nuclear structures with a deposition rate of 80 kilos an hour and a total final part weight of 79 tons. And this was utilizing 14 different welding wires and a submerged arc welding process. So of course, it's easy enough just to go faster and faster just by adding more energy and more wires in principle. In our laboratory, we did have a look, or we have had a look at this. This is an example of using what's called twin wire mag welding. So here we have 2 welding power sources and 2 wires that are synchronized so that the arcs don't interfere with each other. You can see even the pictures on the right, the welding torch and the 2 wires that are protruding from the end. We then do a study of where we can get successful deposition. This graph shows the wire feed speed on the bottom, the travel speed on the left, and the equivalent deposition rate on the top. And the blue squares indicate the successful deposits. The yellow one where we got porosity, and the crosses where it was unsuccessful. And you can see by using 2 wires, we can actually get the deposition rate up to around about 12 or 13 kilos an hour. And we achieve or obtain rather wide walls, of course, and also rather thick layer heights. But we are able to successfully deposit at these higher deposition rates. This is an example of a simple structure that's been built at 10 kilos an hour. One of the issues with the building at higher rates is you tend to get very rough surfaces on the outside. So an approach to dealing with that is to use what's called a skin and core. So on the outside, we have a skin, which is where we use a low deposition rate and a fine deposition. And then internally, we use a high deposition rate, but we're not concerned now about the surface finish. This was building for a drilling head. And this is the final part after a manufacture. And you can see it still looks quite rough because it's a mag-based process, but compared to compared to what we had if we didn't use a skin and core approach, it would look very rough indeed. And in fact, you can see the much wider walls of the much wider deposits where we've used the filling strategy. This part is hollow, I might say. It's not solid, as was shown by the toolpath. So going forward, if we have a look at what the requirements for metal additive manufacture in industrial application are, the first, of course, is to have material properties that are as good as existing materials. We need to have full structural integrity with 0 defects, and we need high quality feedstock material. Next, it needs to be simple and easy to use with fast path planning tools with inbuilt process parameters. It needs to be fully automated process with in-process monitoring and control. And we need mature, intelligent turnkey systems capable of making these large, complex parts. Everything I've shown you to date, of course, has been made in the university laboratory using very skilled researchers, which is not suitable for industrial application. And ideally, of course, we'd like it to be low cost, which means high build rates. We'd like a net shape finish, so no finishing steps are required. We would like to have in-process NDT with guaranteed structural integrity, and we'd like improved match materials. So the focus for the recent developments over the last 4 or 5 years has been on making the production-ready systems. And this is what Filomeno will talk about when he follows me to talk about WAAM 3D. So we spent a lot of time working out how to make this process accessible for industry, and we intend to provide that through WAAM 3D, and he will say more about that. So I'd like to finish on, though, is to focus on the future developments, which is the high build rates, net shape finish, the in-process NDT, and the improved materials. So the key point here actually is to move away from commercial off-the-shelf equipment and materials. So everything I've shown you so far has been based around using standard, commonly available welding power sources and welding materials, which of course is okay. It's readily available, it's tried and tested, and of course it's easily put together to build a system. However, it's extremely limited. It's not designed for additive manufacture, it's designed for welding, and it's incredibly inflexible. And so we are now moving into the next generation of DDAM processes where we design the materials and design the processes. And I'm going to give you an example of how we're going about doing that. So what we'd like to do, based around the current state of the art on the left-hand side, is standard wire and arc deposition. That's actually tungsten that we're showing there. And on the right-hand side, you can see a laser wire deposition right at the other end of the extreme, where we're depositing tracks that are a few hundred microns across. But of course, it's extremely slow. So on the one side, we have high build rate, but poor resolution. And on the right-hand side, we have excellent resolution, but we have low build rates. And of course, we need to somehow break the paradigm. What we want to do is be able to take something like our what is now 15 kilos an hour deposition, combine it with our laser deposition, which gives us a net shape finish, so that we have a target then of 8 kilos an hour for titanium net shape deposition. But of course, this also has to have the correct microstructure and properties. So this is just as important. And in fact, if you look at the basics of metal additive manufacture systems, this current paradigm is that the build rate goes as the square of the layer height using a single axisymmetric energy source, which is what is standardly used. So here at the bottom left-hand corner, we have powder bed technology. We then have laser wire or powder. We then have the wire and arc process, and then we have the high deposition rate wire. And you can see the layer height increases as the build rate increases. The problem is that also we lose resolution as we increase the layer height. Naturally, the width of the deposit depends on the height of the deposit. So by the time we get to the very high deposition rate wire processes, our minimum resolution is several millimeters. And not only that, as we increase the layer height, our surface finish also becomes much rougher. So we move away from a net shape finish. So the conundrum is how to fix this relationship. One way would be to go to take net shape processes and make them lower cost. Or our approach actually is to take the high deposition rate processes and make them net shape. Taking what is an expensive process, trying to make it cheap is almost impossible unless you come up with a new way of doing it. Taking the high build rate processes and making them much closer to net shape, we believe is more viable. So how do we do that? The key to it actually is to get independent control of a layer height and width. So we break this relationship between layer height and width so that we have control of them independently. And the way that we want to do that is our multi-energy source approach. So we have several energy sources which all providing different functions. This is just a schematic. So we could have here ES1, it could be a plasma transferred arc generating a melt pool. ES2 is a laser-based system which enables us to control the width of the melt pool. ES3 is something for melting the feedstock material. We might have ES4 to control the cooling rate so that we get the correct properties. And indeed, we could extract heat at the beginning, or we could add heat. So the idea really is to combine these different energy sources in a way that's very beneficial to give us this independent control of layer height and width, and also the thermal field. So the first approach was to combine a laser with a normal plasma process, and you can see that in the video here. The plasma torch is in front with the wire being melted and the laser behind. And we can then take that on actually and use that to build wall structures. And you can see that in the next video. And then when you look at what we get, it looks pretty good actually. So we do indeed get the net shape finish that the laser process promises for us. But there are some issues with this process. You can see we have a very high remelting ratio, and the process is actually very inefficient because we don't have the energy where we need it. And this can be seen here when we look at the results of, for example, this is the effect of the laser power on the bead geometry. And you can see as we increase the laser power, the bead width goes up, and at the same time, the bead height goes down. And this, of course, is not giving us the independent control of height and width that we would like. And you can actually see the melt beads at the top here. And you can see by the time we add the 7 kilowatts of power from the laser, we have a very large remelting ratio. We could keep the total power constant by summing the laser and arc power. So this graph shows you the effect of the ratio between the arc power and the laser power at a total power of 8 kilowatts on the bead width. And unfortunately, you can see we're still getting this interdependence between the bead height and the bead width. And similarly, if we vary the wire feed speed, it also changes the bead height, of course, but it also changes the bead width, which is not what we want. So the way around that is to use, in the first case, to use multiple lasers. We had 2 lasers either side of the plasma arc, so that in this case, we're able to add the energy where we want it to be. So not in the area where we've already added all the energy from the plasma, but either side of that. And when we do that, we're actually able to produce nice deposits, but with much reduced penetration. However, a better approach is to use a scanning laser. So this is the experimental setup for that. Here we have a scanning head. So our laser beam comes in here. It is then scanned down onto the substrate. This is our plasma torch, and the whole lot is moved on this table. And here we have a high-speed camera so that we can see what's going on. Before we did that, we first of all have a look at some modeling activities to see what the effect of the scanning laser is. So on the left-hand side, you can see when we scan at 3 Hertz, by the time we get to 13 Hertz, you can see we have an almost quasi-continuous equivalent heat source, which effectively, when we get to very high scanning speeds of several tens of Hertz, we can generate melt pool shapes and energy profiles, which are almost infinitely variable. So what does that look like? So here we're just using the scanning laser and the arc. This is where the plasma arc is pointed. And in this case, this is where we have the scanning laser. When you look at that, you can see the melt pool here. And you can see that the melt pool is quite wide and has rather an unusual shape, which of course is what we're trying to achieve. And in fact, we could vary the width of this scanning laser to give us whatever melt pool width we desired. So utilizing that, well, you can see here, this is the deposit, which looks very nice. So utilizing that, we can now deposit material. And in this video, you can see depositing material, and we're changing the width continuously. You can see we have this amazing to look at thin rectangular melt pool, which we have full control over the shape of this now. And when we do that, we can vary the width continuously as shown here. So we can now go on and use this to build walls and see if it can be used in real practice. So this is the first layer being put down. We have a very wide deposit in this case. And then this is when we go on to subsequent layers. And you can see, again, we're varying the width dynamically. We're changing the material feed rate to compensate for the change in width so that we keep a constant layer height. So now we have control of the width independently of the layer height, which is, of course, what the goal of our research is. This is what the deposit looks like. And most importantly, we have this net shape finish without having large amounts of remelting and at reasonable build rates. We've yet to extend it to very high build rates, but we're currently proving the basic principles of this approach. And you can see here how we can have independent control now. So this is with a constant layer width of 21 millimeters, and we can change the layer height to go between 0.8 and 3.3 millimeters. And here we have a constant layer height, and we can change the width going from 18 to 27 millimeters. So within this particular operating regime, we can dial up anything from sub-millimeter layer heights to more than 3 millimeters over a range of wall widths of 18 to 27 millimeters. And this is incredibly powerful for DIAM processes going forward. So in summary, in practice, actually, there are no major issues in large area deposition, provided you have the right hardware and the knowledge to manage distortion and cracking. It's just a question really of assembling the correct components, and you can make your components as large as you would like. Higher deposition rates are possible, which of course are very desirable once we go to much larger parts, but the control is extremely limited, meaning they're only suitable for very simple parts. Next generation DIAM processes will feature independent layer height and width and thermal control. We're currently just at the beginning of developing those, and the energy sources and the feedstock materials are going to be designed and matched to each other, which is what we're doing currently through our new program grant. So thanks very much for your attention, and happy to take any questions.
Thank you very much, Professor Williams. Very interesting presentation, keynote. It's amazing the way you always push the limit of additive manufacturing in Cranfield. So, of course, we can open question and answer turn if any of the assistants want to ask Professor Williams some question. Please go ahead. Yes, Professor
Yes.
Mitchell.
Right. Thank you. Very interesting talk. I want to ask a question about something you didn't mention, which was everything you mentioned was very interesting and very clear. But I wondered if in making very large parts, which of course people have been making very large parts for a long time using other technologies, whether there were any special issues in terms of quality control, which you observed. I mean, I'm thinking that, for example, you mentioned at one point about looking at the grain size and the texture and maybe the alloy composition of the material. Obviously, that's something that requires magnification, which I'm just wondering if there's some new challenges there in terms of quality control, particularly if you want to do it in the 100 days rather than 100 weeks.
Yes, well, there are two aspects to that. So the first question regarding the properties, which you mentioned, the challenge there, actually, the properties depend on the thermal field, which is why I was mentioning actually that we need to have independent control of the geometry and the thermal field. At the moment, the thermal field depends on the geometry. So if the geometry changes, your microstructure and properties change. And of course, that's not what you want, because you're going to have varying properties across your part. So what we are attempting to do is define a range of thermal fields, an operating range of thermal fields, and actually to measure the thermal field during the deposition process so that you can prove that you are getting the correct properties throughout the structure. And that's quite a big challenge, I must say, in particular, the accurate measurement of the thermal field during the build process. The second aspect actually is about control of defects. And the normal practice in manufacturing, of course, is to build a part, whether it's machining or whatever you do, and then inspect it. And if it's okay, then it goes through. If it's not okay, it has to be either repaired or scrapped or a concession made. So what we're working with Strathclyde University is an online NDT process. Because with these very large and massive parts, you cannot afford to spend several weeks building the part and then inspect it and find you've got a hole at the bottom. So we want to be able to inspect the part as we build it effectively. So every layer we would do an inspection, check that the integrity is perfectly okay, and then we will continue building. If there are any issues, we would either remove that layer or effect a repair.
Thank you very much.
Maybe another question from the audience.
Could I make a question?
Yes, Arthur, please.
Okay. It's a question regarding the tooling sector. As you know, we are here in the Marinha Grande, where there are a lot of ball making. Usually, selective laser melting is used for medium, small, very intricate with cooling, conformal cooling tools. And my question is if this kind of approach could be used or applied, if you know, or if you already have some experience, to near net shape peak tooling, but also including conformal cooling features inside. If it is possible, not possible, what are your folks about that.
Yes, we think this is one of the key application areas. We have already made conformal channels in parts. This can be quite large channels or indeed fine channels. We made some demonstration parts for tooling for the automotive sector, where the tool has a rapid cooling surface on the top where it's hot formed, and we would say probably down to the 2 to 3 millimeter scale we can put in conformal channels. We currently have a program to make much larger parts for composite manufacture for the aircraft sector. And of course, one of the advantages of investigating this application is it's much lower risk than building all these high strength, high integrity parts for the aerospace sector, which are critical, which we cannot afford a failure. So actually we would like to investigate the use of this process for tooling much more widely. And in fact, I can tell you in the US, it's a very large topic indeed. And most of the focus of their big area manufacture, as they call it, is actually on tooling.
Your mic is muted. Okay. Maybe a last question, or if not, I have one. You mentioned that basically for industry application, there are no major issue in using this technology to produce large parts.
Well, I didn't say about industry, actually. I said technologically speaking.
Exactly. It's the point. And the question is, industry is not using these technologies. Why do you think they are not using these technologies?
I think
too complete.
Yes. So the main issues are, first of all, most of the in terms of large area deposition, which is, I believe, the focus for today.
Yeah.
Most of the commercial systems don't actually really accommodate very large systems. They're still relatively small. But the biggest issue by far actually is it's very easy to sell machines that facilitate the building of large parts. It's not so easy to know how to build the parts. And so the real requirement actually is to transfer the knowledge on how to build the parts from institutions like ourselves to the industry partners, so that they don't need to be experts in how to do this to actually be able to build the parts themselves. And I mean, we can support them to build them, but ideally they need to have the capability for doing, machines need to have the capability to automatically be able to build the parts. And the second issue, I would say, is for anything but simple parts, is the level of automation isn't high enough yet. You still need a skilled operator.
Yes. Thank you very much. Is there another question? I think I saw.
There's a question on the chat.
Okay.
From Thomas
Van Glab.
Yeah.
Okay. Yes. So Thomas asked, hi Stewart, for the presentation, you mentioned you need more specialized resources for the progress. How would you compare feedstock, power source, and sensory equipment?
You mean, well, I'm sorry, I'm not asking you. I assume the question.
Maybe Thomas can
yeah, if he's on.
Complete the question. Or...
So I'm not sure he's
Thomas, are you there? Or?
He doesn't have a microphone.
He doesn't have a microphone.
Okay. Well, I think his question is around the specialized equipment and where it's needed. So yeah. Actually, the only part that's not needed to be specialized is the motion equipment, the platform that the deposition process is mounted upon. That's standard equipment. What needs to change to move from the standard processes at the moment is moving away from welding power sources to properly designed systems that have much higher levels of control that enable you to control the process. I mentioned about the automation aspect and the skilled operator. And this is primarily because at the moment, when you do the deposition, what you have, or what you get is what you get. And there's no way actually of doing very much with it. And so the whole point of having these dynamic systems where you have much higher levels of control is then once you have that, then you can stabilize and automate the process in a much better way. And that's for the deposition part. And then also, as he correctly mentioned, the process monitoring and control. A lot of people are sticking things onto systems and claiming they have process monitoring and control. And in reality, you need specially designed sensors designed primarily for these applications, and just taking a pyrometer or a camera or whatever it is and pointing it at the process and claiming that you have control. It's not actually true. And there is a certain requirement, particularly as we go to the digital twins and other developments that are required in the future, for sensors and process control systems to be bespoke and designed around your deposition system.
Okay, thank you very much. So maybe we can close this first keynote session from Professor Williams. Maybe it's time to pass to the second session, to the second keynote speaker. It's Filomeno Martina. I saw that you are here, Philo.
Yeah, I'm here.
Okay, so thanks a lot, Professor Stewart. I think we can give a virtual applause to you. It was very, very interesting presentation. So, Filomeno, I will do a very brief introduction. Filomeno Martina, it's former senior lecturer at Cranfield University. So you have a good relationship with Stewart Williams, where he researches on WAAM since 2010, and now it's the CEO of WAAM 3D Limited. So you are going to speak about your approach for big parts printing. So I give the floor to you, Philo, please.
Thanks, Olivier, and thanks for the invitation. It's very nice to see you guys again, although it's a virtual event, of course. I have to say that the set of questions that were asked were really helpful in introducing the context of my own presentation. I hope that with the slides that will follow, you will have a better understanding of the limitations that industry has encountered so far in deploying the WAAM process, and how we as WAAM 3D have tried to address some of those challenges. First of all, just a quick introduction from WAAM 3D. We are a Cranfield University spin-out company, so there is a lot of heritage that Cranfield has put into us to make their own tools and approaches available to industry. Our vision is to become the world's most trusted provider of WAAM technologies through the knowledge, the experience, and the expertise that we want to share with our customers. We are a young company. We were only founded in 2018, but at this point in time, through a fair amount of growth, we have already 32 numbers of staff, and we are about to expand into a new unit in the industrial park where we are. So we've been working really hard to make WAAM available to all of you guys. So what are we trying to achieve? Again, going back to the questions that were asked. Well, the first thing is to enable a smooth technology transfer from the organizations that know how to build the parts to the end users. So those people that just want to make parts. And we think that the solution to this is to embed the know-how in the products and in the services. We want to maximize resources utilization, not just the human, but also the capital, because these are quite expensive in industry. And of course, to do that, you need a suitable level of automation. In the context of certifying parts, we want to have confidence in the reliability of the output. And of course, to achieve that, we need repeatability and traceability of materials and components. And then last but not least, we have to have enough flexibility in the systems, in the solutions, to still be able to do research, which is why we need openness. And crucially, the focus for the next couple of slides will be on the user experience. So how someone who is a technician, an operator in industry, needs to use the systems to have a smooth experience and make industrialization as easy as possible. If we look at the components journey, so what we need to do from looking at a candidate part to using it reliably in service, we start from the assessment of the business case. We have to create the preform. We have to do distortion prediction and therefore design the tooling accordingly, then perform toolpath planning and allocate process parameters. There is the machine calibration and what we call virtual print or dry run. Then you actually print the part, post-build quality assurance, post-processing of some sort, and then you actually use it. And to get through this journey, there is a number of activities, tasks, or bits of information that needs to be available throughout. And as you can see from the dots in the table, there is some which are actually self-recursive in a way. So if we start from, and as an example, number 4, the toolpath planning, you need to know how your machine behaves, how your tooling is going to be designed, what your parameter sets are, the kinematic of the machines. So for example, is the robot keeping the speed or is the robot slowing around the corners? How does your power source behave? How responsive is your power source? And then of course, how the material behaves. And then when you go to the print, you need to have visibility over your hardware, your set parameters, again, the same power source behavior and so on. And what you can see again is that if we look at what's available today commercially or the way organizations sometimes go about integrating their own system and developing their own workflow, there is a fair amount of fragmentation with effectively hard boundaries between each of these steps in terms of knowing what's come before and what will come after. And so the idea of WAAM 3D, an ambitious one, was to create and establish this ecosystem in which we place ourselves right at the intersections of hardware, software, service, and materials to try and deliver the first real turnkey solution based on products, services, and materials that we have developed in-house with the support of Cranfield and the academic partners of the WAAM program, with additive in mind, with the WAAM process in mind. So let's quickly have a look at the workflow. I'm going to guide you through all of the steps, showing hopefully how such a tough problem can actually be enjoyable from the point of view of the user. So the first is the assessment of the business case. We have developed a couple of tools, one on life cycle assessment and one on the cost estimation. And what these tools enable us to do is to predict the environmental performances, so material utilization, energy consumption, and CO2 emission, as well as the cost of the part made in production, to compare it with existing technology. Because of course, we know that wire-based DD for the time being is going to be a substitute technology. So by doing this paper study, we already have the answer around the question of, is it going to make my business better? Is it going to save me money? Is it going to improve the environmental performances? The second step is the creation of the WAAM preform. And really, this is the only step of the flow in which we leave the user the freedom to use whatever CAM or CAD tool they might have, because we understand that people are comfortable with SolidWorks rather than Inventor, rather than CATIA, and so on and so forth. So the idea is that you can use your preferred tool to thicken up the structure, add the base plate, and then you export it in step and Parasolid format to go from the final part to what actually will be printed. We have proof of concept tools to do the preform generation automatically using some rules and design for WAAM guidelines, but these are still currently work in progress. The third step is the distortion prediction and the tooling design. And here we use FEA tools, as Stuart introduced earlier on, for things like, example, prediction of likelihood of stress-induced cracking, assessment of the bending or the buckling distortion, how to go about design the tooling to avoid this, what sort of sequencing to deploy in the build, and then finally optimize parameters in terms of minimizing heat input, minimizing dilution, avoiding defects, and so on. And following up from the example that Stuart shown, you can see here the 200 kilograms landing gear in titanium 64 with no preheating, with the gray areas being well above the yield strength of the material, and therefore suggesting that catastrophic plastic deformation will occur there, which is something that we don't want. Or when we do deploy preheating, in this example at 200 degrees, then of course the stresses are well below the yield strength and therefore can be managed quite well throughout the entirety of the build of the process. So as some evidence, Stuart has already shown these components. The Typhoon Eurofighter part, 2 meters in width, so far one of the biggest parts, if not the biggest parts ever made. The first time we tried to build it, we couldn't even finish the second layer because of buckling. And then by deploying those modeling tools, we optimized the tooling and the sequencing, and we could finish the second attempt really successfully. And then on the right-hand side, the same 6 meters long cantilever beam you've seen, obviously looking flat as clamped, but also even after unclamping and with no heat treating, as you can see, dead straight, despite being very long and with a rather awkward material layout. Again, leveraging on our tooling design as assisted by the FE model and on our toolpath planning software, which brings me to the fourth point. So you've got your preform, then you've got to program your machine. Our flow is based on 5 simple steps. Import the file. You can do the slicing using a 2D approach, a 3D approach, or in the near future, also a non-panel approach. The third step is that of the segmentation, a baseline segmentation, or that based on skin and core. Then custom or crucially automatic parameters allocation, and then the file which is outputted can go straight to the machine. So let's have quickly a look now at what this flow looks like. The first image was the final component. Then we've got the preform. Again, we are still in SolidWorks at this point, which is what we use. Then we import the structure in our toolpath planner, set the layer height to 1.5 millimeters. And as you can see, single-sided part, so only one set of layers. In this particular case, I think there's about 70 of them. Once we've got the layers, we go about the segmentation by drawing this segmentation curve. What they do is breaking down the layer into effectively individual building blocks just by drawing these lines with the spline function. The next step is the guide, in which we tell the robots the broad direction of advancement during the trouble. And then we're just going to tell the robot where to start and where to stop, points that are actually inverted during the deposition. And then the toolpath is already generated. Now, because we have an approach called duplication, and because the layers are sufficiently similar, with this approach, this step done on the first layer, effectively all the 70 have been already planned. Skipping ahead a little bit, you can see the fifth and last segment being drawn. So effectively, in a number of minutes, you have already done the toolpath planning of the whole of this frame structure. And the toolpath is generated within our software. In this case, you can see we've chosen intersection start and intersection ends to take that into account when we calculate the process parameters automatically. The program is generated in a language which can be understood directly by our KUKA robot controller, and you can send it to the machine for the printing to actually start. At this point, before you go and maybe cause some collision or some damage to the equipment, typically what we do is a dry run. So we run the process without actual printing happening. That needs to happen on the machine. But what we can do now is doing it virtually. So we've worked on a simulation package which will do some collision detection. And as you can see now on the right-hand side in the log box, there'll be a warning saying there is a collision between the end effector and the jig. So we need to change the home position. And now you can see again, the rotator was set in a wrong way and the collision was detected. And then finally, the third example is of a printing process running smoothly. And then of course we can monitor the speed, always virtually, what point we are doing in the overall file and in the overall toolpath plan. And then if we want to speed this up, we can act on the speed toggle to save us some time and make sure that the entirety of the print can be completed with no costly damage to the hardware, even before the machine is turned on. And in fact, on the same system, on the same computer where you have generated your toolpath plan. At this point, we're comfortable in going ahead with the print. And here is where the connection between what comes before toolpath planning, trajectory generation, and automatic or custom calculation of the process parameters becomes connected to what's on the machine, so the sensors, in the context of knowing what the part needs to look like and what the machine behavior needs to look like. So our WAAM control software effectively logs continuously the primary process parameters and the primary process variables, both dependent and independent one. So you can see on the left-hand side, obviously the dial is moving because we know from the toolpath plan what those values would have been, and then we measure them at any point in time. Once the part is done, in this case, the Typhoon as an example, we can compare channels that show some correlation, or you can zoom in the data, flicker through the layers to understand where things have gone wrong. And as you can see now, by hovering with the cursor over that area of interest, we're gonna see what kind of warning, what kind of alarms were triggered and recorded. That database is stored on a server. You can access this software from anywhere whilst the part is being printed. So you can monitor exactly the state of advancement of your component from remote. But obviously you can also look historically backwards 5, 10 years after the part has been printed to see what happened during the deposition of the particular component. To enable this, it is absolutely fundamental to have a supporting hardware infrastructure. You saw the prototype of this end effector with the local shielding device in one of Stuart's video. Obviously, as One3D, we have industrialized the hardware itself. And here, effectively, what we're doing is not only providing shielding locally, should you wish to do so in the case of reactive materials like titanium, but we're also connecting a number of sensors, some of which are completely new and really exciting to the printing head. So we have cameras, we have automatic wire positioning in the front to ensure consistent droplet transfer modes. But the really cool ones are this innovative proprietary sensor for the live measurement of the layer height. So in real time, as we know, being the achievement of the layer height being one of the challenges in DED, by having the sensors on board, we can continuously, and while the process is printing, ensure or at least monitor that we are getting the layer height that we wanted. The end effector is available in two shapes, the closed one as well as the open one, which doesn't have the local shielding device, and you can use it for materials that don't require shielding, or in case you are using a fully enclosed environment backfilled with argon gas. To give an idea of where we're going next with the layer height, if we use the same sensor in a bit of a different way, in combination with galvo scanners, for example, we can extract not just the layer height, but effectively the entirety of the 3D shape of the component right during the print. So in theory, we do not have to stop, come with laser scanners or with CMM machines, measure the shape, and then decide what to do. We can continuously monitor that while the printing is happening. And what this does is, of course, increasing the effective build rate, increasing the effective deposition rate while you're making the part, as well as giving you confidence in terms of quality assurance, and potentially informing downstream processes like machining already without having to do any further scan before doing the machine post-processing. All of this would be meaningless if it wasn't part of a turnkey solution, a real One3D system, which is what we've been working hard on for the last, year or so right now. The system will have a number of tech features, again, which will streamline the user experience. So again, not just a combination of welding equipment, but a real machine tool designed with additive in mind. So things like the fuel management system, automated gas purge and evacuation cycle, the in-process filtration, the gas cooling, and of course, safety and monitoring system, which will enable, first of all, automatic operation and therefore freeing of the supervisor's bandwidth, standalone installation on the shop floor with full health and safety compliance, and effectively a plug-and-play installation. And the idea is to launch this commercially Q3 this year. Last but not least, our wires. If we use bad wine to cook, then the food will not be as tasty. And this is the same in WAAM, in additive manufacturing. We are creating mechanical properties, microstructure, and geometries at the same time. We've tried several wires available commercially, and then we have identified some effectively key quality metrics such as cleanliness, integrity of the surface, straightness, stability of the chemistry, that all will have a meaningful impact on resulting mechanical properties. And as you can see from these cross sections on the right, also on the stability of the deposition. And so for almost 2 years now, we've been proposing commercially our premium wires designed for WAAM. Aluminium, magnesium, scandium has been a phenomenal success, but we also have 2219 and soon titanium 64. So going back to where I started from, and just to conclude, so the question, what are we trying to achieve? The embedded know-how, our response to that is to have automatic parameters calculation, smart toolpath planning, the simulation package, and of course, the company's know-how that can be transferred to the customers via technology transfer programs. In terms of automation, one planner for toolpath planning, one control for monitoring and quality assurance, all of the advanced sensing hardware I've shown, all brought together by our turnkey machine tool. Repeatability and traceability, again, via one planner, one control, the hardware, the machine, and crucially also thanks to our premium certified consumables and wires. And then last but not least, the concept of openness. The machine is large, 2 meters by 2 meters by 2 meters. And of course, if you want to use new materials, if you want to use or do your own research, you can certainly override our automatic parameters calculation and do customer process parameters input. So in summary, as Stuart shown, we've been working on WAAM at Cranfield since 2006, and we have certainly demonstrated that the potential to change the face of manufacturing is certainly there. WAAM 3D has been established to create a supply chain for the process, and we're quickly moving from the young kid around the block to having an excellent team and developing new products that will be announced commercially in the next couple of quarters. And of course, we are crucially unique in providing what we see as the right answer, an integrated technology ecosystem that can help you guys along the entire journey. So if you want to have more information, don't be shy, just get in touch on the email or give me a ring or LinkedIn. And in the meantime, I hope you enjoyed the presentation, and I am happy to take any questions in the shortest term. Thank you.
Thank you very much, Philo. Very interesting example of industrial approach to bring to the industry some industrial solution to, like Stewart mentioned, to give the opportunity to the industry to use industrial solutions to manufacture real parts. So maybe we can have a short question and answer sessions. Is there anyone in the audience that want to begin with the questions? If not,
how much does one cost?
How much does one system cost?
Yes.
we can't say yet, but we want to democratize additive manufacturing, and as we are a substitute technology, as I said, and the capital costs are certainly meaningful in terms of how much it actually costs you to put down a kilogram of material. We're gonna be responsible, and the price of the machines will be as accessible as we possibly can.
It's Olivier. Philo, you spoke about certification or certified part. How your solution could, because I think the main problem, at least for aeronautics, it's about certification. How your solution could help to have certified parts?
At the moment, what we have seen with a number of OEMs is the desire to work on a frozen set of hardware and software configuration. The idea is that you identify the critical variables that you want to monitor. There is a little bit of a debate on whether this is the current or the travel speed, you know, the standard welding parameters, maybe the melt pool size, to look at something a bit more advanced. And then once you've printed the first few test artifacts, which are used for mechanical testing and certification, then provided that you can demonstrate repeatability for parts in production, then, and that of course, all of them right now are inspected for cracks, lack of fusion defects, and inclusions of tungsten, for example, then the resulting parts from there onward should also be qualified. So our idea of WAAM control is that by monitoring the parameters that will have certainly an impact on the thermal field and therefore on microstructure and mechanical properties, and you do that for every part that you print, in combination with the compulsory up to today inspection processes, then the industry should have enough confidence that the subsequent part, if printed in spec, will also behave in a predictable manner.
Okay, thank you. Do we have any other question from the audience?
In the meantime, while maybe someone else thinks about questions, I have to say that I will have to leave in a couple of minutes because I've got other commitments throughout the day. So apologies if I don't stick around. But if anyone wants to ask something or get more information, just give me a shout offline. Obviously, we only had 15 minutes today, and the breadth of what we have been trying to do is such that each slide can be dissected into an hour-long discussion. So maybe a lot of things seems like assumptions or bold statements, but do not hesitate to get in touch with me separately.
Okay, so if there is no more question, maybe you can let you go to other meetings.
Thanks everyone. Thanks for the invitation.
For the presentation. Could be very interesting how you go ahead with your solutions, and we can give a virtual applause to Philo. Thanks a lot. So if I'm not wrong, now we have a short break that was planned by the organization, around a 15 minutes break. So maybe we can go for coffee or something like that, and come back in 15 minutes. So at 11:30 West time.
Yep.
Okay. So see you in 15 minutes. Thanks a lot.
Hello, Geoffrey.
Hello, everyone. Again, so I think it's 30 past 11. Maybe you can go back to the presentations. So the next speaker is Peter Hakvist from Procada. Good morning, Peter.
Good morning.
I will do a brief introduction. So Peter Hakvist is a co-founder and CTO of Procada. So after starting his research studies in additive manufacturing in 2010, Peter has focused his professional efforts on monitoring and control of laser wired DED. As a GKA in aerospace employee, he significantly contributed to the adoption of automatic control solution, enabling new applications. During his years in automotive, he worked with strategic technology projects and system architecture for active safety patents, safety systems on senior management level before starting Procada. Peter is an innovator and a researcher with a number of patents, patent application, innovation, and scientific publication to prove it. He's also a jack of all trades engineer who enjoy full stack AM system development in both software and hardware. So it's very impressive curriculum, Peter. So I give you the floor for your presentation. Thanks a lot.
Thank you. I will try to share my screen now. Okay, thank you for that kind introduction. So I will be talking about adaptive process control for large-scale direct digital manufacturing, or DED processes in more particular. So I represent Procada, and we are a small startup company based in Sweden. We're specialized in laser wire DED control. We provide systems and system designs for laser wire DED. We also provide control solutions, both some ready-made products, but also bespoke control solutions. And we also offer services and training. The founders of Procada, we have pioneered this technology, and we have put it into production during the last 15 years. And it's let's say the fruit of our labor is now in production in aerospace for critical components. Unfortunately, most of the things that we have done in the past I cannot show, but there will be some parts of it that I can show, and I will try to show as much as possible today. So first of all, I would like to have a discussion around the DED processes from a control perspective. What are the challenges and benefits of adding control to a DED process? And I will use the laser wire DED process in the examples that will follow. So a DED process in general is time variant, which essentially means that it's not the same process from one time instance to another. Things change. So the dynamics of the process are not constant, which when you compare it to classic control theory, you typically have constant dynamics, but we don't. Why don't we have constant dynamics? Well, it's because things change. We, for example, have a fixture that could heat up, and that will decrease our cooling rates, which will affect things in things that are coming after as a chain of events. If we change the wire feed rate, for example, we will also change the bead height, which will change the laser absorption, which will affect the bead geometry, which might require some change of wire feed rate. So we have these cyclic couplings as well. And also a DED process appears to be non-causal in the spatial domain. And that's a lot of fancy words, but it essentially means that what you do at one instance on one layer will afterwards appear to have happened before you actually did it. And why is this? Well, it's because the material flows backwards in the spatial domain. So as I try to illustrate in the figure here to the right, that if you at one time instance increase the wire feed rate, for example, by a step, the material will flow backwards in the melt pool. And when you look at it afterwards, it will appear as if you started adding that extra wire before you actually did. And this makes it a bit tricky to approach the problem from a time perspective, which is usually the way it's done in classic control theory. And a DED process also exhibits cyclic behavior in the layer dimension. It has a memory between the layers. So what you do on one layer will affect what you see on the subsequent layers. And that is can be both a curse and a blessing, as we will see later on. So, and also a DED process is a multi-input, multi-output system with nonlinear parameter coupling. And this is also very tricky from a control perspective, but let's go through what I mean with this. Well, we start off with having some kind of process, and we feed in a lot of input parameters into that process. We have the laser power, the energy distribution in the spatial domain. We have the wire angle relative to the laser and the substrate. We have the atmosphere in which we work. We have the temporal modulation of the laser, as if we're running a continuous or a pulsed laser. We have the wire feed rate. We have the traverse speed. We have the build direction, the wire position relative to the substrate, and the laser angle relative to the substrate. And also we could have preheating of the wire, so-called hot wire. And all of these parameters, some of them are controllable, some of them are less controllable, all of them go into the process. And then on the other hand, as the output, we get surface roughness, phase composition, porosity, build rate, chemical composition, dilution, distortion, heat affected zones, deposit geometries, possible lack of fusion defects, and the bead geometry. So all of these are the results of the many inputs that we input. And it's not as if you change only the traverse speed, you will change only, let's say, the dilution. All of these are coupled, and they're coupled non-linearly, which makes it harder if you want to control, let's say, only one of the outputs. If you want to make a change on one of the outputs, you'll have to change almost all of the inputs in order to affect that change. And also a DED process cannot be fully state estimated due to some things that are hard to measure. And what do I mean by that? Well, we can't provide at any time instance all of the information that will describe the process at that very time instance. We cannot know all of the relevant information. So as Professor Williams mentioned before, the temperature distribution is hard to measure. You can measure the temperature field on the surface, but measuring the temperature, let's say, distribution inside a piece is even harder and will require some kind of simulation. You also have the stress distribution in your part, which is hard to measure. The material composition is hard to measure, and you could have plasma material interactions. The laser absorption is hard to measure, and also the melt pool geometry. Some of these things are inherently hard to measure as from a measurement perspective, but some things get even harder to measure due to the fact that we have a very high power laser and maybe a plasma and very high temperatures nearby. So we are limited to non-intrusive methods, typically optical methods that are quite easily disturbed by the plasma and the high power laser that we use. So to sum this all up, it's really hard to control a DED process automatically with consistent quality. And by control here, I mean that you should just press a button and it will change all the parameters automatically in order to get the result that you desire. But this is really hard. So I have put down some postulates regarding DED control. You might disagree with me. I would be happy to discuss it later on, but now I'm just going to read them to you. So the constant process parameters will fail when the setting isn't constant. By that, I mean that you have to change your process parameters. You cannot lock in and say that these are the qualified process parameters that we'll use for any application with this particular material, because your geometry will change your temperature field, as mentioned before, and that will basically make sure that you don't have the same setting. You don't have the same system anymore, so you won't get the same behavior with the same process parameters. And one control parameter affects several properties of the process. So most often you cannot change one input parameter and only get one change in the output. You will get changes in most, or at least in several properties of the process. And I also claim that if you get a catastrophic failure, which is something that leads to either the fact that you have to stop the process or you get a big porosity or a lack of fusion, I claim that those failures are either due to poor offline programming, so the preparation of your program, you've started very far from the substrate, or you're crashed into the substrate, or you have entirely faulty laser power, for example. Either that, or that the catastrophic failure is actually detectable and reversible during earlier layers. Because if you keep tight control of your process, you will not really be, these things shouldn't come as surprises. You will see trends and you will be able to mitigate those trends if they are not what you want to see. And connected to that, the large changes in process parameters are to be avoided. Instead, I propose that you use small incremental changes and you distribute over several layers. So, for example, let's say that you have a small void in one layer for one reason or other. Now, when you pass that the second time or the subsequent layer, do not try to fix the entire void or to fill it in. Rather, increase your wire feed rate slightly and maybe repair 10% of the void. And then on the layer that follows, continue to repair 10% of that void. By doing so, you will have a more stable process, and you would know where the void is. So you could just keep coming back to it and keep making the small repairs until it's gone. And for full automation, I also claim that a holistic fault-tolerant system design is required. And I think this ties back to what the earlier speakers have said today, that you can't really go with commercial off-the-shelf equipment. You need to design your system as a whole with all perspectives in mind. And you need to make it fault tolerant if you want to go for full automation. You can't have only single point of failures in terms of both sensors and sensor processing, for example. So then how do you control a DED process? That was the whole point of my talk today. So the most common way, and I think most of you who have worked with DED might have tried this kind of controller. A human, often a skilled operator is a good way to control a DED process, but the problem is that they are hard to come by, and they offer poor repeatability. You can't really, even if they are persons who can be trusted generally, you can't trust them to consistently make the same, come up with the same quality. And also they scale poorly. It's hard to, if you want to double your production, it's hard to find just another operator which is equally as skilled as the one you've already got. So we have to get away from this. We have to go into automatic control. And I specialize in what's called adaptive control, and that is a control method that can control a system which has varying characteristics and varying dynamics, since the adaptive control scheme adapts to the control system automatically when it changes. And I will go through a couple of examples of this. So the first one is called iterative learning control, which was first applied to DED several years ago by my colleague. And it's a process control framework based on machine learning, and it incorporates a learning mechanisms that adapts to local system dynamic variations. So you have some kind of sensor input that will indicate to you if there's some disturbance in one layer. And then during the subsequent layers, you will make a small adjustment in based on some say knowledge, a priori knowledge that you have of the process. You'll make a small change, and you will see what happens to that change, and you will then deduce the system dynamics from that change. So you keep on exciting your process by making changes and try to push the process in the correct direction. You could say that you have all along the path of your tool, you're having individual controllers spatially distributed. For example, wire feed rate or laser power, etc. And the result of this is that, as you can see in the graph to the top, you have a red line, which is the conventional open loop feed forward. No, sorry, it's not feed forward. It's just an open loop deposition of this small knob that you see on the bottom. And after 10 layers, it fails because you get so high deviations exceeding 1 millimeter. But when you engage this iterative learning control system, you could build successfully up to 35 layers and keep on going, because it does adjust to the local changes in especially material, how the material flows and how the heat builds up towards the center, because it's built in a spiral pattern going from the outside to the inside. Another example, which I've worked a lot with recently, is wire sensor based control. So here we combine the concept of using the wire tip as a sensor probe, which is an extremely robust and cheap sensor probe, but we use it also for process control. So the fundamentals of this is quite simple: that you measure electrical signals, you apply a voltage or a current, well, both actually, and then you measure the resistance, for example. And if you have an infinite resistance through the wire, you have some kind of droplet formation. You're not in contact with your wire to the substrate. And if you have a very low, uneven resistance, you typically have what we refer to as wire stubbing, where the wire is scraping onto the substrate when it's in solid state, and it will typically cause lack of fusion defects. So these are quite noisy signals with poor resolution and specificity. So and by that I mean that you can't really measure, for example, the standoff distance linearly with this technology. And a lot of things affect the resistance signal. But we, as I mentioned, we worked with this a lot, and with some smart system solutions, we have achieved some astonishing results. You could see on the left, it's a part that we are currently building a demonstrator for a customer. It will become even larger. It's a single wall that we've built tilting to the right, but we've built it on a plate that we've deposited with this technology earlier, which is 6 layers in width to the bottom, and it's also angled slightly, and we built this onto a hub. So this entire thing has been built onto a pipe to make this sort of bucket. But the truly astonishing thing with this is that we don't have any other sensors than the wire tip probe. And we have reached an accuracy of roughly 0.1 millimeters. And using this approach with a hot wire probe, we've also started building custom hot wire sources. And I was very happy to hear the previous speakers mention that we need custom equipment, and we've seen the same thing. And we've started to develop custom equipment for laser hot wire in order to get more efficient use of the laser and the hot wire, because the hot wire has 100% more or less energy efficiency, and it's much cheaper, but you need to have it under tight control in order to not get arcing and a lot of spatter. But we've managed to do that, and we've effectively doubled the deposition rate with the same laser power using this technology. And last, out of my examples, I will mention adaptive process stabilization, and this is for a coaxial feed system. And on the top right, you see the sequence of a tool moving first left to right, and then upwards, and then right to left. And you could see the numbers 1 to 7 referring to different portions of this sequence. And looking at the 2 rows of images below, you see the top row shows the images for the process without our feedback control enabled, or the process stabilization. And the bottom one is with Procada's process stabilization activated. And in the top one, you could see that the tool is moving towards the end, where it detaches from the substrate. The wire does not touch the substrate, and this will lead to this will lead to a buildup on the wire tip of a big molten drop, which will get even bigger and absorb more laser radiation. It will keep building up until it gets stuck on the nozzle, and the nozzle has to be basically scrapped. On the bottom, we have exactly the same scenario, but our process stabilization activated, and then you could see that we do not get the buildup of this molten metal onto the wire, but instead the wire in a controlled fashion goes back into the melt pool, and the process can continue. And I will finish up with some recommendations for working with DD control. And the first one is regarding sensors. I have seen, especially in academic papers, there is a lot of really impressive sensor setups, novel solutions. But I think it's important that you divide your sensors into two groups, and one is the sensors to learn from, and the other is the sensors to use in production. Because some of these very exotic novel sensors, they're very useful for learning and gathering knowledge, but they perhaps aren't robust enough to be in a production setting. So, and the sensors to learn from, they can be fragile and suited for lab environments. They can obstruct the process partially, or they could limit the applications due to bulkiness or ease of access, or due to some expensive equipment. And the sensors to learn from, they are less restricted by costs for purchasing, maintenance, and operations. And these, I argue, should be used for control system design input. So they are used when you learn how to build your system and how to design your system. And then there are the sensors to use in production, and they must be robust and suited for a production environment. They must not obstruct the process or limit the application, and they must fit into the application business case, so they cannot be very expensive. And these should be used for the control system input. So the information that you feed into your control system, that in turn controls your process. And the next point regards data logging. I am a strong advocate of logging all the data that you can in a structured and accessible way. I advocate either HDF file formats or some kind of databases, and make sure that you time synchronize your data so you know that you could go back and compare different signals at the same time instances, and use appropriate sampling rates for the phenomena that you're investigating. And that means that if there are very quick transient phenomena that you want to monitor, well, then you have to monitor that with a high sampling rate. But most DED, say, relevant signals aren't that high frequent. So you could typically measure, for example, temperatures and positions with something like 10 or 20 hertz. But if you measure, for example, electrical signals from in an electrical arc, then you might want to go into the several kilohertz or even higher. And the next one regards system design. And I think this is really key, and it also ties into what I've heard before, that with the commercial off-the-shelf equipment and welding power sources, that you have to make sure that your deposition system is designed as a system for doing deposition. And you have to keep that in mind when you add something or remove something, that will the system work as a whole. And that ties into the signals which you could get out of your equipment, how you could control your equipment. And we have, for example, chosen to not use any commercial power sources or wire feeders. We've built our own, and we've built our own deposition heads, and we built our own processing chambers. We do use industrial robots, but we are actually looking into changing that as well, to go to fully customized system. Repeatability in system design or on your system is key. And if you can't repeat, you cannot also tell chance from causality. So you don't know what is what. So you need to have a stability in your system so that you can repeat your experiments and repeat your results. And for full automation, as I mentioned earlier, you need redundancy and robustness. So you need complementary sensors with different failure modes. So probably not all of your sensors should be optical. Probably not all of your sensors should be electrical, etc. So you need to have different failure modes so that they don't all fail at the same time. And then last, I want to speak a bit about the human-machine interface. And I think a lot of people make the mistake to underestimate the importance of the HMI. To have an intuitive view of the process is really, really important when you automate it, because I believe that presenting information to a human is the first step of automating it. So you need to give a human a sense of what is this process, what is important, what happens, what causes what, and only then can you start to automate it. And also I'd like to say that a good video says more than 1,000 words. It's super important that you get a clear picture of the process. And most often a bright LED and a matching bandpass filter with an ordinary camera is enough. There are some really impressive well camera systems with illumination lasers, etc. They are useful in some cases, but most often, if you have a bright LED and you have a good bandpass filter and an ordinary camera, that is most often enough. Thank you.
Thank you very much, Peter. A very interesting approach. For me, it was the first time I saw your presentations. It's very interesting. So we can open the question and answer turn. If there is some question in the audience to open the debate, please go ahead. If not, I can begin. You mentioned that one of the approach you have for control, it's a machine learning system, machine learning solutions.
Yeah.
I think that for using machine learning models, you need a lot of data. How do you manage to have a sufficient number of information to be able to run the machine learning algorithm or machine learning system?
That's a very good question. And this type of machine learning is not based on artificial neural networks.
Okay.
It's not based on artificial intelligence. It's another discipline within machine learning, which is causal and predictable. So we could actually use this with the background knowledge that we need is some kind of system identification of the process. So we need to know how are, for example, wire feed rate and process or laser power coupled to the things that we need that we want to control. So if we want to control the temperature, we need to know roughly what is the coupling between the laser power and the temperature that we want to control. That is the type of information we need. And then the system will in itself adapt to the process and make changes. So if you have a local heat sink, the system will learn automatically. So you learn during processing and not before. And I've seen a lot of approaches where you try to feed some kind of artificial intelligence system or neural networks and train it. And then, as you say, the amount and quality of training data is essential. But we've taken a slightly different route, which we think is more predictable and also more transferable to new applications.
Yes, thank you. Very, very interesting approach, in fact. Do we have some other question? It doesn't seem so. You mentioned also about human-machine interface.
Yes.
Do you use some UX design or some ergonomics approach to set up your applications, or how do you manage to adapt the HMI to the user?
Well, we have a framework for developing this, and we build our HMIs in a web interface. And this means that we could quite easily add and remove things from the interface for different users. So you could log in with the specific username, and that will give you your profile with things that interest you. So you could get different information on the screen and all have different views. And we also have the opportunity to what we call real-time rewind. So as you run the process, you could actually step back and look at what happened 5 seconds ago or 20 minutes ago even. As you run the process, then you go back into live, so you could go back and forth. And I think that's been a very good tool for us, and we are able to adapt the HMIs to different users and different, both research and production actually, with the same framework.
Okay, thank you. There is a question from Professor Williams.
Hi, Peter. Thanks. That was a very interesting talk, and of course, I agree with pretty much everything you said, of course. But and actually, you know, you and I have been in this field for a long time, and know from bitter experience actually that these off-the-shelf equipment doesn't work in any kind of reliable manner for an industrial production environment. But I just wanted to ask you, am I correct in assuming that for your positional sensing, you're just using or only using, I say not just, only using the wire resistance measurement into the melt pool?
Correct.
Okay. And the second question then, are you attempting to measure any temperatures or not?
Yes.
Okay. The next question is how then?
Well, we try to be as let's say application agnostic as possible. We have been working with applications where you set up pyrometers, and you could get that working quite well if you're building, let's say, straight parts or rotationally symmetric parts. But we want to be able to have truly, let's say, free-form 3D printing, and then we cannot have pyrometers since they are not spatially resolved. So we're trying to look into primarily what could we do with the camera information that we already have at hand with our visual camera, but then also thermal cameras.
Okay.
But we try to keep it as limited as possible in terms of sensors, in terms of the number of sensors that we introduce, because every sensor is a new point of failure and adds to the complexity of the design. And we know from experience that a skilled operator looking at the process, a video feed of the process, can tell if the process is getting too hot or too cold. So the information is already there. It's a matter of, let's say, extracting it. And you could do that to a certain degree of accuracy, of course. And if you need more accurate measurements, I think an IR camera is the way to go. Mm-hmm. Preferably then integrated into the optics as well, to keep as a nimble instrument as possible, or nimble tool.
Yes, I mean, I would agree with you about the number of sensors actually. And, you know, I've worked for many years, tens of years in laser processing, and many people have tried to put in control systems for welding, and frequently the manufacturing engineer turns them off because they start doing things that he doesn't understand. Yes. And cause problems. So it's absolutely fundamental that your sensor system needs to be simple, but most importantly robust, and not prone to give you errors due to unforeseen variations. Yeah.
And I can imagine we also apply sensor fusion with the sensor that we do have. We apply sensor fusion to make it more robust as a whole, to make the sensors complement each other.
Not independent. Yes. Okay.
Yeah.
Thank you. Very nice talk. Thank you.
Thank you, Stewart. Maybe a last question. I have another one. You seems to have worked a lot with lateral feeding for the wire, and you have also explored some coaxial.
Yes.
Also feeding. What is your recommendation about the feeding of the wire?
Well, I think that the coaxial tools are easier to start with, since you don't have to really take the direction into account. But then you have these other problems, as I showed, for example, with a droplet going up and getting stuck in the nozzle. And also, of course, the limited power rating of these. They are still more complex. It's more complex equipment and lower power rating that you get with compared to the side-fed ones. We have made very successful experiments with steep angle side wire feeding. So it makes the tool act as a truly coaxial tool while you are still having the cheap and robust ordinary optics and the side wire feed, but you feed the wire at an angle which is almost well, not parallel to the laser beam, but almost. But that requires really quick control and modulation of all these signals. And one thing that I would like to add now that I heard what Professor Williams mentioned earlier, with the decoupling of the width and the height of the bead, and that we are starting to explore another way of doing it, and is to increase the traverse speed radically. And that, of course, limits the let's say deposition window. The process window becomes very narrow, but with quick control and closed loop feedback, we could actually manage that. So you could keep, to some extent, you could keep the width with the help of the laser, but you could build, let's say, thinner layers by increasing the traverse speed. And then you add the material required for melting the wire, you add through the hot wire source. So, but that requires very quick control of the wire precision and also the hot wire power.
Okay, thank you, Peter. It was very interesting.
Thank you.
I think we can conclude your presentation. I propose a big applause for Peter. Thanks a lot. We can go through. Maybe we can go through to the next speaker. That is Fabien Poulain. It's a colleague of mine, so I know him. He's going to speak about modeling and simulation. So Fabien, it's as a PhD in mechanical engineering. After some years spent in the machining industry as a process engineer, he is now working as a research engineer at Adimado, a research platform dedicated to additive manufacturing process development located in France, in Bayonne, southwest of France. He's mostly involved in DED process modeling for thermal and thermomechanical analysis. So Fabien, please.
Okay, thank you. Thank you, Olivier, for the introduction. Good morning, everyone. Okay, so today I'm going to talk about modeling, especially part distortion estimation in DED. Before doing that, just a few words about Adimado. We are a young platform located in the southwest of France, dedicated to large size manufacturing of AM parts. And we are currently a small team, 5 engineers, 2 PhD, working on basically 3 processes. We are quite lucky to have a broad type of processes going from powder laser to wire arc and wire laser. The content of my talk today will focus more on process simulation. I will explain a little bit about classical simulation, which relies on a thermomechanical approach, and why we need to move to another paradigm because of its cost. This is the use of light and distortion estimation that will be presented next, and an application to a part demonstrator. So in Adimado, basically, we try to use simulation for 2 objectives. First one is to be able to understand things at the specimen scale, so some bits, in order to see the influence of the parameters on the thermal field and mechanical fields. In order to do that, we use basically a standard transient thermomechanical model. We are also interested a lot in predicting things on a larger scale, especially distortion, in order to answer several questions regarding the clamping strategy that should be used, how to put the substrate with respect to the final part, how to order the layers, especially for double side deposition. And we would like also to have a good idea about the residual stress, especially because most of the time there are following processes such as heat treatment and machining that have to be carried out. So in order to do that, the standard thermomechanical model is actually a good candidate, or could be used, but is much too costly. So we need to find a way to be faster. For the ones that are not familiar with process simulation in DED, I would just talk briefly about thermomechanical simulation. We actually basically have this overview with three physics, thermal, mechanical, and metallurgical, that are strongly coupled. But most of the time, we neglect most of the interaction to move from a strong coupling to a weak coupling. In Adimado, we are using a finite element solver called Morpheo, where we have welding toolboxes and we can run parallel computation. Most of the time, the geometry of the part is simplified, and we mainly deal with a macro scale approach, neglecting complicated physics happening at a smaller scale. Regarding the thermal model, this is something that is very well known at a macro scale. The main difficulty comes from the nonlinearity of the coefficients that have to be taken into consideration, making the cost even high for this simple physics. One challenge is to properly calibrate the model. Actually, the model is well known, but its calibration can be tricky, especially if we have a particular way of clamping the part, etc. So that there are some thermal exchanges that are not so easy to consider. Nevertheless, with this kind of model, we can obtain interesting things regarding thermal history in small size geometries. Calibration is most of the time limited because of the difficulty already mentioned by the previous speakers of measuring temperature. So most of the time we use a contact measurement with thermocouples, which are, let's say, enough to perform a correct calibration of the models. As far as thermomechanical is concerned, actually it works quite well, giving a good tool to estimate distortion. The problem is that this model is very nice, but is not adapted to very large components. You see here an example of a very large, or not so large part, but a larger part that was simulated only thermally. Total time for computation, only thermal, was about 10 days. And thermomechanical simulation would have taken around 50 days if we were to run it. So clearly, even if you use a bigger computer, you face a big obstacle when trying to use this kind of model on large components. So this is the idea of moving from transient thermomechanical model to lighter modeling. There are several options. The one we've tried to use in Adimador is inspired from inherent strain. So inherent strain was a method originally developed for welding in the 80s, I would say, by the Japanese researcher, and that was adapted more recently to a powder bed fusion simulation. The idea actually is to replace the complex thermomechanical loading by an equivalent loading and to apply it into an elastic, simply elastic model. There are two ways of doing, either to rely on calibration specimen and do reverse engineering, or a second option is to try to calculate the inherent strain by reproducing a representative configuration. In both cases, it ends in identifying an inherent strain to be applied on the full component in order to derive the distortion. We've tried to transpose that to DED. So in order to do that, we've to take into consideration some specificity of DED. First one is that the building strategy might be 5 axes, which is not the case in PB in powder bed fusion. The direction of deposition might be much more variable. So we try to run a bid-based approach. This strain direction has to be taken into account and adapt to each bid. And finally, as I mentioned for PBF, the options, calibration or calculation are today more limited in DED, and we most of the time rely on calculation. Here is an overview of the strategy that we use. The inputs are the trajectory, so the CAM program, material properties, and process parameters. All of this feeds a local model, which is actually an elementary model on a small size component. This always, or as much as possible, relies also on calibration, so we try to check the validity of the local model. From this simulation, the strain evolution during the process is analyzed, and we try to feed an inherent strain database. Finally, we come back to the final full part scale and map the identified inherent strain onto the large part. So by doing that, we can progressively simulate the loading that is applied to the part and evaluate the resulting distortion. The idea is to progressively, as I said, enrich a database and finally only use this database to perform the inherent strain mapping on the full part. So do not run a local model that can be quite time consuming. Well, this kind of model is applied mainly to one class of parts. Here I made the distinction between 2 kinds of parts. On one side, the stiffened plate, where a small amount of material is added on a large substrate with a large footprint, and in comparison with an extrusion class of part that will have a lot of material deposited on a substrate which is much smaller. Why is this applied mainly on the stiffened plate? Because it's easier to apply and maybe more adapted for that kind of parts. Most of the time, the interlayer time is quite long due to the large part dimensions, and there is an efficient thermal dissipation in the substrate because of the volume of material and the contact with the tooling. In that context, we consider that an incremental simulation, bidwise most of the time, can be carried out. We usually perform the simulation in 2 steps. First one is to consider a more or less stable scenario, consider that interlayer temperature is quite stable, and apply a relatively constant inherent strain tensor during the construction. This allows us to do a first analyze and compare some layer ordering strategies. When some good candidates have been identified, we try to refine the estimation by taking into account local specificities, as you can see here, things that can happen at the junctions on this kind of part. We try to increase the fidelity of the predicted displacement map. To finish, I will show an application of this approach to a part demonstrator, which is a purely symmetric stiffened plate, let's say, with a tooling only at the periphery, allowing for rotation of the part during the process. We've run simulation in order to answer 2 questions. How are we maintaining the working distance in a given range and acceptable range around nominal distance? And is it possible to minimize as much as possible the number of rotations? So as you can see here, first simulation of deposition of layer 1 on side A shows low distortion. Layer 2 is also deposited on side A and shows a higher distortion, but still in the range that we've defined a priori. When we add the third layer, we see that we start becoming out of the range of plus or minus 2 millimeter of displacement. And this means that in that case, deposition on the other side is required to move on with the process. And we've done that incrementally in order to derive the best scenario that fulfills both objectives here. After that, the simulation of the unclamping stage was done, and we see that between an optimized layer ordering and a non-optimized one, there is a lot of difference in terms of distortion. One is around 4 to 5 millimeter, and the other one is around 1 to 2 millimeters. In terms of computational time, distortion simulation here is transformed into a sequence of elastic calculations. Each time we run an elastic simulation, it's around 1 minute. So you have the example, for instance, on a wall made of 20 layers, which is not a complicated configuration, but with a standard thermomechanical model, the time for the computation is about 1 hour per layer, so 20 hours. In the case of the inherent strain model, it's more 20 minutes, even if the, let's say, the result of both models are not the same. But if we are only interested in distortion, we see that there is a very interesting gain in computation time. As far as the demonstrator I've shown is concerned, the simulation was taking about 10 hours, which is a lot, but still acceptable time. So the idea, well, is, as I mentioned before, is to construct a database for this inherent strain, because what I don't mention here is the time that is required to run some local models in order to derive the inherent strain. If we consider this time for computing the models, then the effective speed-up factor is actually less than the one we see in that table. What are the main limitations of that? The main limitation is regarding the residual stress estimation. Why? Because it's quite sensitive to the distribution of inherent strain that we use in the model. Actually, the equivalent body force that we consider is based on the derivative computation and requires some transfer of data from elements to nodes, and it is a source of error. This is also the case for the estimation of surface force acting on the part that require very good approximation of inherent strain locally. So most of the time we have observed a magnitude of displacement that is quite well estimated, 10–15%, but a lot of uncertainties remain on residual stress estimation. And it's so difficult to validate because of the difficulty of measuring residual stress that, well, today we don't trust this model to have a proper residual stress map. So the way to the ideal simulation tool that would be able to do some process chain like DED, heat treatment, machining, to be sure that the part has always correct geometry to move on to the next process is still very far. We bring some contribution for the first step here, mostly evaluating geometry after DED, but there are still a lot of unknowns to be defined. Well, this is the end of my presentation. I thank you, and if you have some questions, do not hesitate.
Thank you, Fabien. Very interesting presentation. It seems so easy when you speak about it, but it's not. So maybe we have some question from the audience. I see the presentation of Sebastian, but I don't see if there is any hand. So,
hello, Olivier, can you hear me?
Yes, Sebastian.
Yeah, can you see my presentation?
Yes, but we have you have to wait just 2-3 minutes more because we have to ask a question maybe to Fabien.
Okay.
So, do you have any question for Fabien?
From my side?
Not for your side specifically, but from the audience. So, Fabien, maybe what are the next steps to go further? You mentioned that you have to include maybe treatments and machining, but
yeah, today the idea would be to get a more interesting evaluation of residual stress, because yeah, the DED process, the WAAM in particular, in which we are interested, requires heat treatment and then machining. And by knowing in some ways the residual stress resulting from DED first, it's possible to derive what could happen during heat treatment. Distortion could happen during heat treatment because of stress release. So this makes the result of heat treatment very uncertain. Even if the distortion is acceptable after DED, we are not sure that it will remain acceptable during the whole chain of process that will come after. So this is, I think, a key challenge. Another challenge is to deal with extruded parts. I mentioned that most of the time this approach is applied to stiffened plate, as I call them, with small amount of material deposited on a quite large plate. With higher deposition in terms of number of layers, this type of approach might be more difficult to apply and might require more work, and we will lose the gain that was expected initially to derive, especially this inherent strain map on the whole part. So maybe there is also a compromise to be found for these other types of parts, and maybe inherent strain is not the perfect approach for that. So there are still many things to do if we want to have a reliable numerical tool for large parts.
Thanks a lot, Fabien. So we can conclude your presentation.
Sorry,
applause for Fabien.
Sorry, Olivier, I just had a question as well, or a suggestion.
Okay, sorry, Stewart. Yes, please.
Just to let you know, I mean, we use the inherent strain method as well. Actually, you might want to consider only needing to use it for the first 3 or 4 layers, and rather than just looking at the actual distortion, to make a continuous comparison against the critical buckling load to see if you get buckling. And then beyond the first few layers, actually, buckling doesn't become an issue. What becomes an issue is cracking. And for that, actually, you can switch to a very simple shrinkage model rather than a full FE type approach. And we find this works extremely effectively in working out how much bending and potential cracking you might get. So it's just a couple of bit of information really about how we go about doing large parts.
Okay, well, thank you. Thank you for the suggestion.
Thank you, Stewart. So we can go with the next presentation from Sebastian team. So we can see your presentation properly, Sebastian. I will do a brief introduction. So Sebastian has a diploma in mechanical engineering from Dresden University and a degree of international welding engineer. He worked as a scientific assistant of University of Dresden in the Institute of Manufacturing Science and Engineering. He worked also as the group leader for laser wire deposition in Fraunhofer. And since 2018, he is a founder and CEO of Coax Works. The company is going to present right now. So please, Sebastian, go ahead.
Okay, thanks, Olivier, for the introduction and also for inviting me for this short presentation. Hopefully the presentation is in full screen now. Yeah, okay, thank you. So yeah, I want to give you a short outline. I first want to go into the wire LMD technology. Then I want to show you the 3-beam laser head we have developed during my Fraunhofer times, and what now we are selling as Coax Works to the industry. And I want to show you a couple of examples what's possible with this process and technology. So today we have heard a lot about wire arc additive manufacturing. And so we at Fraunhofer IWS in Dresden, and also with my company Coax Works, we just focusing on the laser metal deposition. I know in the audience are a lot of experts, so I don't have to go too detailed. We use the laser as energy source. We have shielding gas at environment, and we use metal wire. These are compared to the 3 other technologies which also can use using wires, but we don't want to go too deep in this. So the wire LMD technology is basically a single-step metal deposition principle, 100% wire utilization. And we are focusing in the coaxial principle. That means we have a rectangular wire and laser beams from the side. And there are a lot of principles on the market with 2 beams, 3 beams, 4 beams, or ring beams. We in Dresden always focused on the 3 beams to get the omnidirectional process guiding. As you can see here in the scheme, an additional DC current can be attached to increase the building rate for this process. On the bottom, now we have a short video how the on-the-fly process is basically working. Yeah, during real parts, we sometimes have combined stationary start and flying end, sometimes stationary start and stationary end, or like in the video you have seen, flying start, flying stop operation. Yeah, basically we also come from the normal welding background where wire diameters in range of 0.8 to 1.2 millimeter diameters are used, but we also going to increase the wire diameter, and what was really also a need from the industry during the last 2 years, we're also going to decrease the wire diameter. Maybe it does not fit exactly to the today topic big print, but maybe it's also interesting for some of you. So we also looking forward to go down for thinner wire diameters, 0.4, and already in the beginning of this year, we have done for an industrial customer 0.2 millimeter wire diameter trials. Yeah, we come from the surface cladding background, and later we have seen, okay, we can use our technique also for additive manufacturing, feature adding and repair tasks. And basically, in the last years, we have tested a very wide range of wire materials. So I always say, if the alloy is available as metal wire, we can use it for the process. A short overview about the 3-beam laser head. We have developed in my group during the Fraunhofer time, and now it's our main product as CoaxWorks startup. The head is possible to use diode, fiber, or disc lasers up to 4 kilowatt laser power. We have the 3-beam optic principle, and yeah, it's a compact design based on 1-inch optics, and with periphery like wire feeder and camera, we have a weight of 50 kilograms. And we focus in the development of an easy and user-friendly adjustment. I want to show you in the next slide, but first, please see here the main beam concept task in the near process zone. So you can here see more better the 3 beams coming in 120 degrees to one triple focus. We have a free distance of 85 millimeters, but basically we're working with a stick out of 10 millimeters. And on the left side, on the bottom, you can see a focus measurement with a Primus focus monitor. Here made with a diode laser with 600 micrometer fiber. We get a 2 millimeter focus. And this is, for example, very sweet able to operate a 1.0 millimeter wire. In the head, some very important technical features are built in, which you need for long-time processing. The most important, and it's also the USP of our product, is the near process safety and collision shutdown. Number one, that means we have built in a module, this one here, that allows, in case of a collision of the nozzle with the part, or in case of cold welding of the wire, that the lower nozzle part is tilted up to 7 degrees. And the module is coupled with a safety stop of the machine. And so basically up to 5 meters per minute travel speed, and the machine can stop and without any damages at the head. So after that, the operator can cut the wire or move slowly out of the collision zone. Then the sensor is going back in the normal position, and right after a minute, you can go on with your processing. Maybe a check if everything is right is necessary. If something has tilted strongly, we have built in number 2, X wire, YZ wire supply adjustment. So if small adjustment is necessary, we have a very precise adjustment here, and the operator can modify it. Then, of course, a lot of you know there are some crazy steel alloys which have a lot of splatters and a lot of smoke during process. For this, we have built in a cross-jet number 3 for each of the 3 beams. And we have also down-jet for smoke protection of our cover glasses. So, let's just to let you know, there are some add-ons available, like the hot wire. And you can see here we have a water current cable that's come from the outside, and it's isolated from the rest of the head. So you can bring an additional energy source and combine laser with resistance heating. We don't have a hybrid process, so no arc and laser, it's just preheating. And I have seen in the last presentation of Fabienne, some of you already use the chilling gas environment. For this, we also have a tent interface where you can adapt a foil, and for example, for titanium alloys or for inconel alloys, we can also work in very high quality shielding gas environment with lower than 20 ppm oxygen. Yeah, as we also have learned in some presentations before, to really get good results in processing, you have to know many details about the whole setup. That's why we also look for our clients about the wire feeding, the monitoring, gas tent, I already mentioned, induction, preheating, and as I told you, we can make the setup right for the equipment that's given, disc lasers, fiber lasers, or diode lasers. And let's say 80% of our clients use robot as machine, and just roughly 20% use CNC machines for their setup. So now we come to the examples. And in the slides, there are mainly movies shown, but always in some of the examples, I have a table where you see the exact used process parameters, laser power, feed speed, and I also have added the cladding rate in kilograms per hour and cubic centimeters per hour, so that you can make a comparison maybe to your wire arc additive manufacturing results. So here we can see an Inconel 625, one layer cladding on a milled steel rod. We have a 1 millimeter diameter and work with an overlapping of 50%. By this, we get a layer height of 1 millimeter. And of course, to get a really good bonding to the surface with no overlapping failures and pores, we have here a dilution of 9% in the middle. And by this, you still can have a 21% chromium content on the surface. That would be ideal for a sealed seawater environment, for example. That was the background behind this example. Then we have here a first multi-layer example. In that case, with a very difficult alloy. In that case, it's aluminium. So aluminium is the most difficult alloy you can handle with this technology, because of the high melting temperature of the aluminium oxygen on the surface, and the low melting point of 650 roughly degrees of the alloy itself. So you have to really look for the heat treatment, and you have to modify your parameters. As you can see here in the example, we have started with a 4 kilowatt laser power at the first layer. And from the second layer, we have taken 2.5 kilowatts. And the production time at all was 50 minutes, but just 23 minutes laser on time. So we needed 27 minutes waiting time for cooling down of the part. And the number of layers was 120. And so finally, because of the low density of aluminium, we have here just 0.2 kilograms per hour cladding rate, or because it's a thin wall structure, and the long waiting time is just 18 cubic centimeters per hour. But after we find out the strategy for this part, it was possible to duplicate the part 20 times without any failure, but to get the process strategy needs us roughly 3 months. So it was a student work, but he works on the strategy each day, so it roughly needs 3 months. So maybe some simulation or control ideas from my former speakers could help in the future. I mentioned the thinner wire. So we have here example with 0.4 millimeter wire, a simple cladding application. But as you can see, for thinner wire, much less power is necessary. So in this case, just 550 watts. And this brings, of course, also just a very low cladding rate. But on the other hand, as you can see in the cross section below, very flat surfaces with a low waviness and the chance to have a very near net shape add-on on certain parts. What we also can see here in the cross section, it was not a power controlled process, so the dilution is getting higher with the process duration. So in this case, the result for the next step was to add laser power regulation with monitoring software. So here is an example what brings the highest energy input, what our head allows. So we have 4 kilowatt laser power, and we have an additional current power from the hot wire of 650 watts. So by this, we get a cladding rate of 2.7 kilograms. That means 320 cubic centimeters per hour. But honestly, this was not a real part. So as you can see, the metal is very bright. It was just for demonstration what's basically possible. This was done at the application center of Fraunhofer in Michigan, US. So the biggest part I can show you in my presentation is this one. We built a 3D nozzle out of Inconel 718. For this, we try to optimize the parameters, and the final parameters you can see here in the table. We have a 2.5 hour production time, but laser on time was just 2 hours. So also in this case, we had half an hour waiting time for cool down because of the thin wall structure of this part. But basically, as you can see in the video here, starting using this 3D 3-axis CNC machine in this case, starting from a 20 millimeter thick plate, we could build up this single layer built up, and we had a deposition rate finally of 120 cubic centimeters per hour. And in this case, we also make the post milling that gives a very good inner material quality. And in this case, we also made some intermediate cross sections to get this. Problem here, and this shows, let's say, maybe the limitation of the technology at all. The inner surface of this part could not be post-processed by milling. So maybe for the future, we will try to use the milling device of this CNC machine so that we have a kind of hybrid processing. And the idea is after each 10 layers to have intermediate milling to have finally also a good surface inside such a thin wall structure. So now we come to the last example. We basically have now seen some rotational parts or some 3-axis machine examples. But I also want to show you that the technology is working on a robot. In this case here, we have a KUKA 30 kilogram robot, which is making a real 3D operation on this small part here. We try to figure out the orientation of the head, that it's always 90 degrees to the surface, and you can see what fast orientation movements the robot has to be done. But basically, because we just have these small features, we made a couple of tests, and finally also such 3D surfaces can be cladded with good quality. So hopefully I could give you a good overview of what's possible with the technology. Yeah, for the future, we are working to increase the laser power. What's possible with laser-based additive manufacturing, because what we have seen in the presentations before, the cladding rate, the build-up rate with ARC as energy source is much higher, and a lot of clients during these days already have 8, 10, 12 kilowatt lasers, and they want to use the high laser power for their R&D. So that's why we currently already working on a high power laser head, but it's not yet ready to show you here in this presentation. So thank you.
Thank you, Sebastian. We are a bit out of time, so maybe we can, if there is some quick question, maybe we can take it. If not, we can go to the next speaker. So I don't know if there is some question. It seems not. It was very interesting in your presentation, the way you can print aluminum with a laser. So it's quite interesting. So thanks a lot for your presentation.
You're welcome. Thank you.
So now we can go to the, we are just 5 minutes late, so we can go to the next speaker. So next speaker is Peter Tommy Nielsen. I think you are here.
I'm here, yeah.
Okay, yeah, welcome.
Thank you.
So I will do a brief presentation. So Peter, you have a background at the blacksmith and in chemical engineering. You have been with the force technology for 13 years.
Yes.
Your department consists of highly skilled manufacturing professionals. Their expertise range from R&D to experience-based best practices and production. And the goal is to obtain the best possible solution with financial aspects, sustainability, and functionality at the drivers. Focusing on the product, optimal production, method, and capabilities are extended through industrial expertise at Additive Manufacturing Link. So yes. Please, Peter.
Thank you. Thank you for the very nice introduction, and thank you for inviting me. I have also been listening in to the previous presentation, and it's very, very impressive, I think. I will talk about 3D printing in a large scale environment, which is very industry driven. Just to outline what I'm going to talk about, I will address force technology just to give you a little bit better understanding of how we actually work and why we have this system as we do, and what is our focus? How do we print and for who? And therein you find all the motivation that is for sure well known. We all want to do a little bit better on the cost and lead time, and the new buzzword as well, sustainability is also very, very important. So I hope you have a few questions afterwards also, because I do have something which is on the borderline of deep R&D also, something that is very, very difficult for us. Even though we are working with the local universities, sometimes yeah, we get a little bit stuck. So please feel free to shoot me down afterwards. Very, very briefly, we are a Danish RTO company, and yeah, there are several of them in Denmark. And I will say, if to compare on a European scale, we are somewhat similar to Fraunhofer. Although we have a focus on Scandinavia as the primary area, but we are also located in the Arabics and China and Singapore as well. I'm sitting in Denmark. Our print facility is also in Denmark, but not in the same place as our headquarters. It's on an old shipyard called Lindø, which closed down almost 15 years ago. And in Denmark, we took a political decision. The government took a political decision to spawn this old shipyard into life again. And today it's actually bigger than it was when it shut down. Yeah, I think there's approximately 150 companies present at the shipyard, and the employees numbers must be around 4,000 or something like that. So it's a really good thing for the local area. Just some very fast photos. We have a lot of our turnover is from international customers as well, and almost half of it. We are 1,100 employees and doing quite good, I think. The most interesting part, I think, this is this one. We have over 400 unique facilities, and one of them is the print facility, and yeah, that's quite amazing. And to understand why we do have so many facilities is that we do not have any shareholders. So every time we earn some money, we make a profit, we invest in new technology. And the new technology is something that will reflect the society's need within a 5 to 10 years frame of work. Okay. Yes, this is also some corporate stuff, but I just want to say that almost everything we do is concerns around this business. We do a lot of things just because it's fun and interesting and necessary, but it's very rare that we do something if it doesn't have any business scope. So that's very, very important for us. So our capabilities and facilities, the department I am head of is actually an old welding department, and that is the foundation of force technology as well. We do know a lot about welding technologies and also how to qualify and make sure it goes well. We do a lot of coding technologies, and all of these things in this department pointed in the direction of well, maybe we should go in full-scale AM, and not just regular additive manufacturing, because we actually had access to all the welding technologies as well. So this is how it looks, our facility at the shipyard. It's I would say it goes as one of the biggest around. I would say that might not be true, but it is special. It's special because the size of the booth is quite big. It's 8 by 7 by 4 meters. Half of that is filled with the manipulators, as the latte, tilting turntable, and the robot on rail. We are able to perform welding, hybrid welding, and normal arc welding. And this, of course, points in the direction of 3D printing and surfacing and repair work through arc welding or laser cladding. And we have the capability of blown powder, 3D printing, as well as wire fit. The new thing for us in this case is actually the feeding system over here. You don't see my mouse, I can see, but you know the feeding system of the blown powder. We didn't know that that well before we started in combination with laser technology. But as I will show you later on in this presentation, it actually performs quite well for industrial applications. Inside, we have the capability of several tons of component size. It's a standard industrial setup. There's nothing magical about that. But I still do think it's very impressive that you can have a tilting turntable that can hold a 1 ton heavy cubic meter in tilt mode and still be stable. And this is something that our system can do. We do have activities within additive manufacturing, 3D printing at full scale, but the most of our work is actually focused on remanufacturing, fixing worn out high value components. This has been mentioned a few times. You are probably all very much experts in this field. What I can add on to this is we do use blown powder. We have learned a lot since we started in 2015 within this technology. To enhance the deposition rate. We started with maybe, let's say, 1 kilo per hour, and we are working in the ballpark of 4 kilos per hour now. So it's very much interesting for the industry as well. And now I will go to a case story. This was also the front page of the slide. I have to mention that even though we are called Force Technology, we are not within defense. We are an RTO company, which happens to work with companies who are, for instance, making parts for this F-35 jet fighter. This was also something that started in around 2015, 16, around there, and was one of the cornerstones of deciding we need to qualify this process, and if we can, we will definitely invest in this system. So we were looking at what can we actually achieve. Well, we should be focused on reducing the material consumption as well as the process time. The economy is also important, but the lead time, as we hear it in our industry, we are in connection with if we can optimize especially the lead time, that is a huge benefit. And I also have a small video here. At this time we made this, we were working together with a German company producing this device. This device is mounted on the F-35. I can't tell you what it is, I'm not allowed, but as you can see on the slide here, if you were to machine it, you should start with approximately 220 kilos and spend a lot of time on that, or you could 3D print it with 9 kilos and be ready within 4.5 hours. So that was quite impressive. When we started this work, we didn't know software that well, but we did know robot programming. Regarding our own facility, that is has been until now our Achilles heel. The CAD/CAM software has not been good enough, but now it's significantly improved, I would say. So we have an add-on to our system, quite a long ID cladding head. It's 1.1 meters long. This is also something we do with use in connection with industrial work, as well as our R&D, but the primary focus on the industrial work. The idea is here to combine different material properties. In this case, as shown on the pictures, it would be nice to combine something that has a high heat transfer, thermal conductivity, with something that is wear and corrosion resistant. So we do that, and of course also for cost issues. And I have a small video of that ID head in operation. This tube is just above 2 meters long. This also means that we have to approach the coating process from both sides. And it's always interesting to go in a tube with this long cladding head. You never know, shouldn't go wrong, but it's always a little bit interesting. And here you can see, as you all probably, most of you know, once it's in, the process is quite, yeah, not that impressive. And this is how it should look. Yeah. We also have integrated the WAAM process using a CMT machine. We did that to meet some of our special areas within the architecture. Yeah, and let me see. We found a software that could do the job. As you can see in the picture, it's from MX3D, and the first KUKA robot equipped with that. And these pictures are from the installation where we made a nice vase. But what we are working on now is something quite different, and I'm not sure if this is something we will do again. It's very special, I will say. This is a city model from an area in Stockholm, where we are collaborating with the big Bjarke Ingels Group, which is a Danish international architect house. They came to Force Technology to address how they could make such a city model. And there was, of course, many options and possibilities here. But if you should consider all issues that could happen with such a model, maybe it would be better to just make it in metal. And we decided to, in collaboration with them, to of course do that. We are starting the work on a 700 kilo heavy build plate, a big boy, as we say it, in Denmark, and it's almost 1.5 meter in diameter, 50 millimeters thick. And on top, we are putting 500 kilos of build material. And I also have a small video of that. And before I start that, so you have a different view of the booth. You can see that half of the equipment actually fills the half of the booth, and that's our intention of the design, because we do have a lot of different applications that will not fit in a standard setup. So sometimes it's some rollers or other manipulators we are fitting in the booth, and in this case it's just a simple table. And yeah, it looks fun. It's a GoPro movie, so it goes fast and very stressing to look at for hours. Let's see how it goes. So this is something that is actually going on at our Lindø facility today also, and we are expecting to finish this model within a little more than a week. And then we have the installation in August from the customer side. Yeah. Working with the industry, the first thing they ask after they have asked about the cost and lead time, they will also know a little bit about the quality. And as you know, working with welding technology, it means also that you will have some sort of defects, and that will at least affect the mechanical properties. So in general, I would say when we look at a new material, then we would like to decide how our feed material should behave, and which particle size we should work with in that specific context. This is actually from the F-35, and as you can see, everything seems to perform pretty good. But if we want to avoid a spatter, then we shouldn't go up in size. If we go very low in particle size, we will experience some, or could experience some difficulties in keeping up a constant feed of the material. So we chose a particle size between 22 and 53 micrometers that seem to be working fine. We also have done a lot of cross sections looking at all possible ways to find defects, and for this material it doesn't seem to be any issue, especially when you address important step of post-treatment, how the isostatic pressing, as you probably are familiar with. So the microstructure is good in all directions. Regarding the mechanical properties, you can also see for all sizes in this regard, they are actually doing quite good. And for our customers' perspective, they were all acceptable. What I didn't include in this presentation, which I could have, just remember that now, is we also have done a full fatigue test program on this component. And this is also on expected level. But this is a military standard we are up against, and I would say they are on the conservative side, but very close to the standard levels. the important thing is that it's acceptable, and the deviation from the standards is something that you can address by designing and taking lowered values into account. We also did something very different in this regard. We did a hot tensile test at the 600 degrees. This was done because of the specific application. It tends to be a little bit hot, so the customer also wanted to learn if the values actually would be the same at its temperature. But the standard didn't describe this at all, so we had to make some sort of a parallel study from the literature, and could see that there's nothing strange about having lowered values at 600 degrees Celsius. So what we of course are asked also, is it reasonable to look into 3D printing from an economical perspective? And I will say in general, it depends. What are the alternatives, and could you do something else, and maybe you can focus on enhanced performance, etc. You must look for the benefit at least. We have a lot of different examples. The light blue bar here represents the F-35 application, and we can see that we could do something about the lead time. We actually have quite a large reduction on that. And as already indicated, the material consumption is also lowered significantly. So that's a huge benefit. What we do not what we cannot pinpoint in this diagram is that it's the same component we are producing, so the part number will be the same. What is not included is the price level, because that is something that's very difficult to talk about, but I can outline it here. We're actually looking at a 40 to 50% price reduction. So it's very attractive for this application. We're also working on the rocket nozzles at Force Technology in collaboration with a lot of different companies. And if you make the same comparison here, yeah, the part counts has reduced from, I believe it's in the area of 1,000 components to about 100 in one rocket nozzle setup. So it's very attractive. And of course, it's also something that can be manufactured a little bit faster. Price level follows that. And yeah, the final bar is within the power plants. In Denmark, we do have a lot of waste incineration plants, thermal power plants. And we have demonstrated a method for them that for instance, for burner nozzles, that you can with some reason go and remanufacture those for a fraction of the cost price. These are components that usually are casted, and they usually have an extremely long lead time. So it's very attractive for them as well. I will say this is something we do for almost any new component we are working with together with the industry, just to evaluate what is attractive for this specific component. I would say you also always have to just challenge the specific component and the customer. What is actually in it for you? Would it be better to do machining? I would say many times it would be, but as the times are now, maybe not. material prices are increasing. It's difficult to get a hold of the materials you want, and most of the SMEs in Denmark anyway are not willing to build up their storage with expensive materials. So maybe this is a reason enough to look into additive manufacturing. And then the classical stuff, yeah, what is the alternative? It's either milling or casting. Yeah, but when you do casting, you're also very fast to lock on design, and that is not always the best idea. Something that has not been released from Force Technology yet is a small study we recently did on bronze. We actually made a direct comparison from one cast of bronze and a 3D WAAM printed bronze, and then we did tensile testing. And I'm still scratching my head a little bit about the numbers here, because as you can see on the slide here, the mechanical properties are not that good for the cast materials. And that could be very problematic if you're making a propel or for something for a submarine or a ship or something like that. Of course, we do have one explanation for that, at least. Within casting, which has been around for somewhat like 2,000 years, also have some difficulties within making cavities and voids. And this is, of course, the explanation of lowered performance. But very interesting, and if some of you have looked into this area, I would like to reach out to you to share our findings. It's very important for the local companies here in Denmark. Some of the new initiatives within the large-scale print facility we do have available at Force, also triggered by the material corona crisis we have. This is around gears in many different sizes, but the thin red line is large gears, also for an area as wind turbines, which is a very big thing in Denmark. We have 3 companies in a small consortium working on how to make these gears better or repair friendly, and of course in the end demonstrate that this is a reasonable thing to do, also to put in the nacelle in a wind turbine. As you all can imagine, if we have a failure for just one tooth in a wind turbine, then you need to replace the entire thing, and the cost of doing that is astronomical. So we have to do a lot of work in that area. So if you have any experience in this field as well, I would also like to hear from some of you. And that was basically everything for me. I don't know if I hit the time or not. Please answer or ask questions for me.
Thanks a lot, Peter, for your presentation. A very interesting approach in introducing financial data. Also, it could be interesting for Industry 4.0.
Yeah,
we are just a bit late, so but probably we have time to have some question. Any question from the audience?
Yes. Yeah, I have a question.
Yes.
Right, thank you, Peter. Very interesting. I wonder if you could just say a little bit more about the rationale for making this architectural model from metal, because you showed I guess a design which seemed to have a much better surface finish than you would be able to achieve. I wonder if this is for artistic interpretation or
Yes.
something else.
This has been some sort of a learning curve for us as well. We are usually working with machine parts and things that should look nice and shiny before we put them in operation. But we are working with this new branch which finds welding seams very beautiful. So it's attractive for them to have this extra element of design in their surfaces. So that was the major reason, and secondly, something about durability and it will not break if some angry persons hit it or something like that.
Okay, thank you.
Yeah.
Okay. I have a question also. Maybe you have, you mentioned that it's a big cell you have to print parts. You have some different head and some different solutions. At least I saw a blown powder head and CMT head.
Yep.
How do you choose the right process for the right part? Or do you have some hybrid approach also? Or?
Yeah, we do have a hybrid approach, but that's primarily within welding technology. We would in general like to work with a blown powder if that's our first approach, to see if this is successful, because we have a little bit higher deposition rate. We seem to have a little bit better quality, and we do have some flexibility in the material feed. So that would be choice number one. Yeah. Does that answer your question? And yeah, secondly, we take into account what else could be relevant. We also use a wire feed, and we use that from side feed, and have done that for many years, and it works fine, I would say, very good. But we seem to hit a certain level where we cannot feed anymore. And that level is a little bit higher within blown powder for us anyway.
Okay, because you are very focused one. You are there is some big parts, very big parts, like the gear part or something like that.
Yeah.
And probably wire head, it could be better than blown powder head. So it was why I asked about the choice of the process. No, it depends on the geometry of the part, on the size of the part.
I would say at this stage we are at now, I would say it's a lot of it's influenced by tradition. We seem to have a better economy within blown powder compared to wire fit, but then again, wires are generally a little bit easier to handle, and also a little bit cheaper. So this is an influence factor. And working on big parts, it's really difficult to avoid defects, and wires seems also to have the magnitude of the defects can be a little bit larger, and thereby also more critical.
Okay. Thank you. The other problem we faced with blown powder, it's also some healthy consideration. It's more tricky to use blown powder for healthy consideration. So, for instance, in our facilities, we are working specific room, and using wire deposition, it's quite easier.
Oh, it's a environmental thing. Yeah. Okay. Yeah, I understand. You have to be able to address that, and it's also difficult. We usually do. It's the biggest problem is around when you feed the system. you pour materials in the container, and you can get some devices that actually do that in a closed
Loop.
loop, yeah. Or you can take the powder feeders off and put it in a room, but of course that's a little bit more work to do. For now, we haven't had any problems with dust or anything like that. We recently made a analysis of our air environment to see if it met the standards of at least the Danish scale, and it did. We are below the levels.
Okay.
Yeah.
Thank you, Peter. If there is no more question, maybe we can just stop here for this session. I think now there is a break for lunch, and we are going to go back at 14:45. So we have 1 hour and a quarter, and so I hope you appreciate the presentation. I think it was very interesting, with some new things for me at least. So have a good lunch, and see you at 14:45. Thank you very much. Right. So it's 14:45. So we are waiting for Arthur, but I will begin.
We can't hear?
Yes, I think we can start. Could you hear me? Or... Could you hear me properly?
Yes, Olivier, we can hear you.
Okay, so it's a problem from Geoff probably. Okay, so we can begin for the afternoon session. So this part, it's about printing big with plastics. We have 2 keynote speakers. So the first one is Emil Johansson from RISE Institute of Sweden.
Hello.
I will do a brief introduction. So Emil has spent the last 6 years developing the innovative additive manufacturing processes at RISE Research Institute of Sweden. His main focus has been software development for large-scale additive manufacturing using industrial robotics. Since January 2021, he is the CEO of Adaxis, the French-Swedish startup developing the next generation software tools for robotic 3D printing. Sorry, Arthur, I began for you. Your mic is off. Yeah.
Thank you very much, Olivier.
I've just done the brief bio from Emil, and Emil, you can start when.
Okay, excellent. Thank you very much, Olivier.
You're welcome.
Thank you very much for that nice introduction. I hope everyone is very revigorated after lunch. It has been a fantastic day of a lot of interesting presentations. I feel a lot of pressure, to be honest, because there are only a couple of presentations for plastics. So I will try to inspire as much as possible of what is possible to print in large scale in plastics. My name is Emil Johansson, and I'm have spent, as Olivier said, the last 6 years working at Research Institutes of Sweden as a project manager within additive manufacturing. And very recently I joined forces with a couple of fellow additive manufacturing enthusiasts in France in order to start a company called Adaxis, where we are going to develop software for robotic 3D printing. I will give a quick sort of overview of my journey in additive manufacturing. So I started out actually printing the tiniest things that you could possibly imagine, technical ceramics. Then I had a brief stint of working with automation of metal printing. In fact, this is when we are trying to clean powder from parts using acoustic vibrations. So it's a signal horn. After that, I realized that robotics is actually what I really want to do. So I've spent now the last few years working primarily together with ABB Robotics in order to develop 3D printing using their robots, specifically for thermoplastics and short fiber composites. So of course you might ask, why would you be interested in using robotics for 3D printing? And I might be preaching to the choir in this setting here, but obviously it gives a lot of really nice advantages. So you have the ability to perform 6-axis material deposition. They are perfect for integrating in existing environments. And of course you have full flexibility in terms of what you can put at the end of the robot. I think we've seen that today, where we will also see some concrete printing later in the afternoon. Apart from this, they are also widely available. There are about 3 million robots in the world today, industrial robots. So there is quite a big potential to turn this into to 3D printers. At RISE, we are quite proud to have been one of the pioneers in this technology. Started out about 6 years ago, working with ABB Robotics to develop software to be able to use them very efficiently as 3D printers. And we've printed a lot of really exciting parts. I will show you some of these today. Everything from chairs to automotive parts to, I think it might be the world's first rocket engine made out of biocomposite. So I'll get back to that. So we have a physical and virtual test and demo environment, meaning that we have the equipment that you would need to print huge parts, 6 by 2 by 2 meters. And we try to sort of work with every aspect that you would need to succeed with robotic printing, from material to quality assurance. Everything that we do is related to some of the steps that we've, I think, seen also in metal printing today: design, simulation, process planning, programming the actual robot, monitoring the process in real time. But also, since we are quite good at thermoplastics at RISE, we do a lot of work on the actual materials and how to adapt them for large-scale 3D printing. So in this presentation, I will talk about 3 things mainly. So the good and the bad of the printing of huge parts. What are the challenges? What are the exceptional possibilities that we could have? I will touch upon the topic of path planning, how to use the robot to its full potential. And I will also introduce a little bit about what we will do in this new company that we have just started, the spin-out company. But first, I would like to take you through this short video to show you what the environment is at RISE. So we have built up a physical environment now for the last 6 years in order to be able to manufacture innovative parts within all kinds of industries. Since Sweden is a country of forests, we work a lot with biocomposites, wood fiber filled composites, and we have been fortunate enough to also work a lot with outdoor products, for example, kayaks. We have an ABB robot equipped with a high throughput extruder. We're able to program it using ABB Robot Studio software, where we have contributed to the development of their software tools. This, in fact, is one of the biocomposites that we regularly use. It's 20% wood fiber in PLA. And as I said, we've really been fortunate enough to work with a lot of exciting products. So one of them being outdoor products like kayaks. And here we worked with, for example, a Swedish company called Melker Kayaks in order to 3D print the full kayak in 2 pieces, but you would then merge them together and it will be possible to use it as an actual kayak, as I think you will see very shortly here. The extruder here is about 35 kilograms per hour. So we have the possibility to manufacture huge parts in a relatively short amount of time. And as you can see here, quite spectacularly, it is in fact possible to print even parts that are being used in water like this one, this 5-meter kayak. So with that short introduction into what we have been doing, I'll just show you another picture here of the kayak. So obviously we have been running a lot of research projects funded by the Swedish government, but also the European Union, this being one of them, where we were fortunate enough to build up our entire infrastructure to do large-scale printing, and worked with a lot of really interesting small-scale companies. One of the really interesting ones is also called PREFORM Design Lab, and 2 associated companies, Svenska Wood and Sculpture, which have developed what at the time was one of the first pieces of 3D printed furniture in serial production. And right now they have ongoing production of these, and it's really quite exciting. These are printed in ABS plastic, for example. And you can see our robot in the background. So this really leads me into my first topic here of the day then. What can we do with robots, and what can we do with large-scale 3D printing of plastics? Well, it gives us a lot of flexibility. So as I said, we are using an extruder at the end of the robotic arm. 5 to 35 kilograms per hour of extruders are quite common to do large-scale 3D printing. We have sort of the upper end of that limit. What we have discovered, in fact, is that really you never need much more than 10 kilograms of material per hour, because after that it becomes too difficult to cool it at a rapid rate. But it's always good to have a little bit of extra power sometimes, especially when extruding difficult materials like wood fiber composites. We feed the extruder with pellets. This makes it very efficient in terms of financials, because we can buy bulk plastics. And in theory, it is possible then to use any bulk material that you could get your hands on. Now this it's actually not true in real life, because you have quite a severe problem with distortion with some plastics. I'll come back to this. But what actually works quite well is different variations of ABS, PLA, polypropylene, polystyrene, PET might even work, and any combination of these with short fiber composites. And since we are, as I said, a country of lots of forests, we have been working with different kinds of biocomposites. The one you see on this picture is in fact 50% wood fiber in a polypropylene mixture. So you have this flexibility in terms of material, and you have the flexibility of the robotic arm. So then you sort of ask yourself what could possibly go wrong. At least that's the way I started out thinking about it. And obviously you start out printing a lot of these very big parts like vases and things like that. I think it's very common in any kind of 3D printing that you start out to that. And obviously you realize that it's not really as easy as it looks, even though plastics are quite a forgiving material if you compare with metals. And it turns out that the size is unfortunately not the only problem. I would also take the opportunity here to introduce my colleague, Lenny Tönning, who is a fantastic collaborator at RISE, and he will for sure be also in some other videos in this presentation. The size is definitely not the only problem here. Big parts lead to big problems. In fact, you could think about it as if you are scaling up everything that you see in small scale 3D printing with plastics, where you just make everything 10 times bigger. So every problem you have suddenly becomes a 10 times bigger problem. Overhangs, quite obviously a problem. You might be able to get around them with a smaller 3D printer, but when you're dealing with material coming out at such rapid pace, even in 12 millimeter strands of material, then you have quite a severe problem with gravity and cooling of this material. And you can always force cooling with the fan, for example, but it quickly becomes a problem because you can't have a massive fan covering a huge area like that. Some materials have a very narrow process window as well. And since you have a lot of built up heat in the materials, you have problem with short layers. So when you come to the end of the print, you will in almost all likelihood have a problem. When you're joining multiple paths during the printing, as in the right picture here, you will also have some potential for problems. So there is this huge flexibility, but in the end, what you have to do is that you have to consider all of these particularities with the large scale printing. Now, the good thing is that unlike metals, plastic is very forgiving. So typically you can have a successful print even with these kind of problems. I just want to highlight what I mean with narrow process window. So in fact, the two parts that you see on the left here, they were printed, it's a polypropylene glass fiber composite, printed at 210 degrees Celsius, 45-second laying time for both. The only difference is the cooling. So obviously the cooling on the left one has made a huge difference, even though everything else is quite the same. Now the problem is, of course, that cooling will also influence the material properties, as you can see on the right. So it will actually negatively influence both the stress at yield and peak load that you could achieve. And it's like a balance between achieving a nice looking print and a print that is actually very high performance. So I just want to show that it is something to really think about, and establishing the process window is very important, especially if you're going to print a huge part, which might be a couple of square meters big. You can't cool everything at the same time, probably. So then you will have to think about tailoring the process parameters to support that. The design also has to be very suitable. We've done a lot of printing of these really nice gyroid structures like the one you see here on the left. Even though in theory it looks like it should be perfect for 3D printing, you very quickly end up with problems that the tool paths are not really adapted to this kind of design. We've experimented with a lot of kind of lattice structure to be able to print huge parts very quickly. But even then you can quite clearly see that you have some interesting defects appearing, for example, in the corners here. And when there is a start and stop, you can expect to get some voids. Now this is, I should say, quite a difficult material to work with. It's a wood fiber composite, but still. Distortion must be taken into account. Leno is in this picture again, so as promised. He is in a wastewater tank that we have printed in ABS on the left. And as you can see, if you know that it's supposed to be flat, you see that it is severely distorted in the middle. Now, if you introduce a bit of fiber into the material, and of course it's quite a different material in the first place, but then you can reduce the distortions. So typically you will see people using these kind of fiber reinforced materials to avoid these problems. A lot of interesting videos have been posted to LinkedIn in the last year on how to do angled printing with thermoplastics. Can solve a lot of problems. So in fact, what you're doing is, as you can see on the right, is you're printing at an angle. It's still planar layers, but you're depositing it at an angle. So you can print overhangs, which might be impossible otherwise, but you will still have to think about what becomes the theoretical top layer, because you're just moving the problem to a different orientation. So it can solve some problems. It can also give you a tremendous bonus in reducing material waste. So we were printing last year a motorboat, and using angle printing, it was possible to reduce the support material for this particular motorboat by 95%. So for the entire boat, we only used 11 kilos of support material, which I think is quite exceptional in terms of material efficiency for this kind of part. I will show very quickly some short video here of what it actually looks like when you're printing something this big. So we collaborated with a boat company called Pioneer and ABB Robots, and managed to print a 4.5 meter motorboat last year in November. Now, unfortunately, I have a difficulty waiting for things, so we wanted to launch it immediately, and we decided then to launch it into the Swedish archipelago in the middle of December. That kind of put some pressure on it to be successful in terms of the launch, but luckily it was in fact possible to, you can see here we take no chances, obviously we're in a wetsuit and a dry suit, but luckily everything worked out, and it was possible in fact to 3D print a boat, launch it, and it worked on the first go. Now, I don't necessarily recommend doing this particular exercise, but it does prove the point that it is in fact possible to print high performance parts in a high performance material. This is a polypropylene glass fiber material, and make it work. Just a second. So this then leads me into the other interesting aspect of using robotics. So the innovative printing strategies that you could possibly conceive using here. You can see some of them on the right here. So we have the angled slicing, but we also have the possibility to do non-planar deposition, as in the upper video here. In order to do that, you need to have the appropriate tools in order to program your robot. We have developed some of them in-house together with our other research institutes that we're working with within, for example, the SoftPrint project. And we then are able to import these paths directly into Robot Studio in order to make it possible to 3D print very efficiently these kind of innovative non-planar structures. Path planning is a very broad topic. I'm not expecting you to read this slide, but it requires you to think about a lot of different parameters that could influence what is going on. Now, there is, of course, a benefit. You can avoid the staircase effect that would typically appear when you're printing especially large parts. But you also get the ability to deposit the material not in a 3-axis way, but in a 6-axis way. So you get the added flexibility of that. Just to show you that it can have quite a pronounced effect. So traditional horizontal slicing versus geodesic field path generation, in this case for the Stanford bunny. I will show you quickly some non-planar strategies that you might think about printing. So the most common one is that you intersect a mesh substrate with another mesh. So you might have a 3D scan part, you want to print on top of it, you have your CAD model, and then you do an intersection test, you generate your tool paths based on those intersections. And it becomes quite computationally intensive, but it can be done, and it is possible to produce really nice tool paths. Another option is to go with what I described as geodesic field distances. In this case, what you do is that you select an origin on a part, and then you generate tool paths on equal distance from that origin. In this case, for this propeller blade here, the origin is at the bottom, and then we get these nice tool paths emanating from the bottom. And there are some really nice software that lets you do this, and LibIGL is one of them. We can also think of what is typically done in metal printing, which would be to align, for example, the tool orientation with the part surface. In this case, it's a rocket nozzle, and as promised, I think it probably is the first rocket nozzle in a wood fiber composite. Now, it will probably not hold up for more than one single use, but it is always nice to be able to say that you were the first with something. In this case, we are also using geodesic distance field, and we have selected the bottom of this part as the origin, and then you can just generate your toolpaths emanating from that, extracting the orientation for the tool from the geometry, and you are in principle good to go. Now, there are some practical considerations here, unfortunately. Printing something planarly with thermoplastics works surprisingly well. Even if you mess up, it works quite well. But when you're going to do non-planar printing, even a small misalignment of the TCP will be a problem, because you have probably with these kind of fill materials a little bit uneven extrusion, and that is going to show up very, very quickly. You also need to have sufficient resolution of your toolpaths, unless you're working with arcs, but if it's a more complex part, you're not able to do that. The toolpath orientation has to be of super good quality. And in practice, of course, since the extruder is quite big, it's not possible to move it as freely as we want. We can't print horizontally, for example. It's not allowed by the material feeding system. We have now for the past year, 1.5 years, been running a research project called SoftDream, specifically targeting development of software for robotic 3D printing. It's been coordinated by RISE with some other very exceptional project partners, SDA being one, TU Braunschweig, Volkswagen Group Innovation, Aerospace Valley, and an integrator in Sweden called Spectrum. It's been funded by AT Manufacturing. Now, I'm incredibly fortunate that we were able to do this project, because out of this project, we were able to launch a startup company called Adaxis. And for the last 3 minutes now, I will tell you a little bit about what we do. So Adaxis is a company, French-Swedish startup, designing software that should make it as easy as possible to turn any robotic arm into a 3D printer, regardless of material. So we think of it that you will select your robot, your deposition head, and then our software will be able to make it work. We have sort of developed everything that you would need to succeed. And everyone in the company is coming from a very practical point of view. We have been standing next to the robot, working with it. We have been trying to use Rhino Grasshopper to do toolpaths, and it works exceptionally well, but it can be quite time consuming on an industrial level. So we have developed this software that puts path planning and process simulation in the hands of the user. You have real-time monitoring, being able to track the process, what is actually going on in real time, and you can keep track of everything from our cloud service. When it comes to path planning, it gives the possibility for 6-axis toolpaths, adaptive infill generation, and of course a robot and process simulation. The manufacturing monitoring is everything from vision inspection systems that we are able to connect to capturing of the real process data in order to recalibrate the robot behavior. And we aim to make everything robot and process agnostic, so that it is possible to use with a Stubbly robot or an ABB or a KUKA or a universal robot if that's what you have. And we hope that we'll be able to add support for concrete extrusion soon. So this is one typical use case, printing of a rear bumper for my Volkswagen Golf. We are 4 people in the company, branch office in Gothenburg. And just to sum up quickly then, large-scale plastic printing is now widely available in Europe, and robots have the possibility to make them even more flexible. You need to understand the process constraints in order to reduce the failure rate. But with innovative path planning strategies, some of which I've shown here, you can solve some of the remaining problems. And I believe this is one of the future manufacturing technologies for large-scale plastic parts. Thank you very much.
Okay, thank you very much. So Olivier, from now it's my time.
Yes, it's your time.
Yeah. Okay. So Olivier, do you have questions or others have questions?
Yes, Emile, you didn't speak about finishing the part or some sort of machining. It's not necessary for the parts you built, or?
Yeah, it can be very necessary. So we have done it for a couple of parts. For example, we've done it for a composite tool that were used to manufacture a composite part for a boat. So it was printed in plastics and then machined afterwards, but not with the robot. It was machined in a regular CNC. Now machining it with a robot is possible, but it can be quite tricky, especially if the part has become distorted, because then it will not be in the same location. And by not in the same location, I mean, it could deviate by 1 centimeter or something like that, depending on the material that you're using. So it is possible, it is quite necessary in some cases, but still a bit of a challenge.
Thank you.
Okay. There are more questions? Okay, I have one question. So regarding the process, there are also some approach where some or others are using a press tool before or after the position.
Yeah.
What you know about that? What the advantages and possible disadvantages for such approach?
It's a fantastic approach. I really love it. In fact, what it does is that since you're typically printing parts with a short fiber composite, the problem that you will have is that even though you're printing it with a composite, the integration between the layers is not going to be perfect. Now this can be improved a lot by using this kind of press that will do this after the printing is like after the material has been deposited. The disadvantage here is of course that you're not able to print freely in 3D because you have to have the space for the press. So it works very well for parts with the traditional planar toolpaths, but it will be more difficult for something like angle printing or non-planar printing. But it's a really nice tool to be able to use it.
Okay, thank you. So now we have a question from Alban Mallet.
Yes. Hi, everyone. Can you hear me?
Yeah.
Okay, thank you. So I'm Alban Mallet, CEO of X3, and thank you for the presentation. It's really, really interesting. And we also are really interested about digital twin, and we have some developments. And so you show some research you have done and some results you had. And I just have a technical question, because we are always wondering what's the best to do a good digital twin. And I think I saw some picture of video and pictures you have taken, and I was wondering if you start to look at online scanning or visualization directly during the print to see exactly what has been done, and not just having the data, but really what have been printed. And if you have like something like online scanning to see between what have been sent to the machine and what have been realized finally.
Yeah, this is a fantastic prospect of 3D scanning the part while you are printing. We have actually thought about this, and we wanted to do it. In the end, what we realized was that a 3D scanner today might be too slow, at least at that level, in order to give an accurate view of what the actual part looks like while you're printing. You could probably do it a few times during the print, but not continuously. An alternative that we have not looked at yet, but it would be to use a line scanner while you are printing, so you can get a sense of what the situation is with the current layer and maybe a couple of layers down, and then you can build that into a geometry, like a complete geometry. We have also used some vision systems in order to try to extract the 3D model. But in the end, what it really comes down to is what is the level of detail that you need. If you only need to have a very broad view of what the print is doing, if you have a huge part, for example, and you just need to know that it hasn't fallen over, that is possible, I think, to do in real time. But if you need to have a high resolution model, like a regular 3D scan model, it will be, I think, at least from my perspective, a little bit too slow to build it up and continuously. We are very interested in this kind of work, so I'd be happy to discuss further.
Thank you very much.
Thank you very much. More questions about plastics? This is only contributing plastics in this all day, so we need to use this opportunity.
I hope, well, that everyone who was previously presenting in metal is now switching over to thermoplastics. But yeah. We'll see what happens. But maybe next time we will have more presentations.
Yeah. There are more questions? So if not, thank you, Emil. Thank you for
thank you very
very
much.
good presentation.
So
thank you, Olivier, for your introduction and everything. And I give you the word again because you are the man on service. You are muted.
Geoff, do you have a question maybe? Or?
Yes, I had a question for Emil. I wondered when you spoke, when you said when you move to large scale plastics, everything multiplies. I'm thinking about this in a more positive way. Perhaps the things that you learn from doing it on a large scale are things which people have overlooked or brushed aside when looking on the small scale, and therefore the small scale printing could be done much better if one was to take account of those things. And I was particularly thinking about when you're talking about cooling. I mean, cooling is obviously in the end one of the key parameters in this, but in actual fact is done in a very simple way. Like, and even in the large scale, you're doing it in a very simple way. And compared with if you were to take the technology that's built into the software to drive the robots or all of these other things, you're putting a huge amount of effort into one thing and almost no effort into something else. And I'm just thinking perhaps the large scale provides us a way of rethinking how to do small scale printing to a better quality and a better, a better way.
Yeah, I mean, this is a fantastic suggestion. I have actually not thought about this in that way, but what you are completely right. The importance of the toolpath and the material deposition, it becomes immediately obvious what is important when you are dealing with such a huge scale. If the robot is moving backwards and forwards after the start and stop, you will see that effect immediately and you understand very quickly. So I think you're really onto something here, and it might be possible to draw some direct parallels to smaller printing. It's a fantastic suggestion, in fact.
Okay, thank you.
So, okay. So Artur says we are now going to concrete printing, right?
Yes, yes.
So I mean, you were the only one in plastic printing. So.
I don't know. Perhaps someone looked to me in a different way, like for a special plastic presentation, a special share.
Yeah.
I think cement is made from polymers.
Okay.
Yeah.
Yeah, but it's Olivier now. So
yes, you can go ahead. It's not a problem. Okay.
Yeah. Thank you, Olivier.
Thank you, Emil. It was very good presentation. I liked it. Okay, so we are going to the cement printing session. So I think the first speaker of this session is Volker Reutinger. Good afternoon.
Yep. Good afternoon.
We'll do a brief introduction. You are the founder of Vertical 3D concrete printing. So before founding the company, you work in the automotive industry, during which you develop a keen interest in 3D printing. You decided to turn your passion into full-time job, and now runs this startup in digital manufacturing. So you are based in Eindhoven, and you mentioned that you have a wife and 2 sons.
It's all true.
So welcome, and you have the floor for the presentation.
Thank you. I will share it. I hope you can all see it.
Yes.
Since we only had one plastic presentation, I can maybe add 2. We actually started, my intention, but before starting Vertical, was actually to 3D print in polymer as well, in plastics, because my experience from the automotive industry, I did a lot of 3D plastic printing projects there, and actually a lot of steel printing too, because we were part of a steel manufacturer. And I actually wanted to do robotic printing with large-scale recycled household plastics, which we managed to do. But at the same time, we also received subsidy to develop concrete printing alongside a construction company and a concrete company. And certainly there was a lot more potential in the market for 3D concrete printing, because the market for large-scale plastic printing, I wouldn't say is saturated, but as Emil said as well, there's a large availability already. So there are many players in the field. With concrete printing, that isn't the case yet, even though in the past year or maybe year or 2, I've stopped being able to count how many concrete printers there are in the world. Before that time, you know, we kind of knew how many there were, but it's really been booming. So we are one of those that has boomed out of the interest in concrete printing. As I said, we were founded in 2018, so in Amersfoort in the Netherlands, alongside the concrete construction company and the construction company themselves, with 2 other companies in Amersfoort. And we've completed 8 projects so far. We're now doing a tiny house, sort of pavilion structure. And we are located in Eindhoven because we moved here because there's a lot of universities, a lot of students here, and Technical University of Eindhoven is one of the front runners in concrete printing. And a competitor colleague of ours in Weber BMX also has a print facility here. So there's just a lot of concrete printing going on in Eindhoven, and with us, you know, it's becoming somewhat of a hotspot for concrete printing. I wanted to show you all a little bit what our facility looks like. I've muted the video because sometimes it doesn't work so well on Zoom, but I'll give you some live commentary. This is our facility in Eindhoven. We have ABB robots running on track and stationary. And what concrete printing is simply a special mixture of concrete that is pumped with traditional mortar pumps through a set of hoses. We use parametric software, Rhino Grasshopper, much like Emil explained, to generate the code. So the slicing, we developed our own slicing software as well. We developed our own concrete mix. And we run this code to the robot and simply deposit the material from a nozzle actuator. And this video was from about a year ago, in which you can see the simple steel nozzle. And that's interesting because in 3D concrete printing, there are basically 2 main ways which you can do concrete printing. One is for the larger construction style objects, and one is for the more fine detailed, and which can go relatively large, but not really with the volume that the construction printing of houses goes, for example. So the reason I say this is that the one technology, basically you rely on the material properties that you pump in order to make for the buildability. And in the other scenario, you add an accelerant at the very last moment, because the material becomes hard within a matter of seconds. And it's if you add the accelerator too early, your hoses will block. So you have to add it late in the process because you want it to set as fast as possible. We do both techniques. We have developed now also the technology for accelerating material at the nozzle. And I will show you more of the technology in the coming slides. What we do is basically 4 things. We sell the hardware, so turnkey solutions of concrete printing for both construction and for more architectural design applications. We have the software developed. We do printing as a service and a lot of consultancy because it's quite a young market. So people still want to know what's possible. Just to show you the technology, this is, as I said, this is the technology where you pump, and based on the material properties, you build large objects. This is a ABB robot on track. So we have a width of 10 meters that we can reach, about 3 meters deep and about 3 meters high. It's the approximate size. If we would fill that volume, we would have an issue that it wouldn't fit out the door. So there's some logistical challenges, but theoretically, that's the area that we can print with this machine. It also prints on both sides. We also have a smaller machine, which we dub our R&D machine. It's a much smaller robot, very easy to move and install. That's popular with universities or with R&D departments to do R&D on the material. This is basically the family of robots we do, from the smaller ones. This is the R&D style, medium ones, mid-level range, and then the larger range that goes on rails, etc. So there's a lot possible in between. What you see here is the second version of the nozzle that is prevalent in concrete printing. This is the nozzle that we developed also, in which we can do adding the accelerant. And what you can see here is 3 different tests to show what you can reach. In general, like printing of concrete in houses, you can basically make straight walls or a 5 or 10 degree angle. And what you can see here is already an angle of over 45 degrees that it can reach if the geometry is right. What you can also see is that the test on the left is the sort of chimney. And this was designed to show how fast our buildability is going vertically. And these objects, all of them were designed to fail. So hoping to sort of test the limits of where our technology would still be viable. And all of them just kept standing and kept standing. So we had to make ever more extreme objects to see where they would fail. So you can see this type of concrete printing is really to do the more extreme objects, which is only really possible when you add this much accelerant at the last moment in your process. So what can you make with this process? This is an example of one of the main advantages of 3D concrete printing for the construction industry. This is what's called topology optimization. And what we have done here is, what we do is we can ask the computer to simulate a bridge that we want designed. So we say, please go from A to B and carry a specific load over that distance. And what the computer will then do is generate the bridge design. So here we have asked to have this length of bridge spanned with a particular pressure for the amount of people walking across. And what the computer will then do is what's called finite element analysis, where it will break this design, basically a block of concrete, into small cubes, and it will subtract cubes basically one by one and test if the bridge will still hold. And what that then results in is a design that's minimized for material use. So you see these holes and structures, which is all the areas where material is not required to carry the load that we specified. What you also then get is very organic shapes. So it's natural, or what's called biomimicry as well. If you look at a tree is devoid of any excess material. A tree is very efficiently grown and has obviously very organic shapes. So these organic shapes are difficult to make by hand and very costly. And that is obviously where 3D printing has its advantage, because the different complexity of elements do not incur similar increase in cost. So in my opinion, we will see more and more of these topology optimizations being done for the built environment. And concrete printing is really a technology, especially robotic 3D printing is a technology that does well in this space. Another example of what we can do is something called parametric design, in which we use this rhino grasshopper modeling, which you've heard about already, to define our wall segment. And it's a good example of this type of project because this wall on the left ended up being shorter and the wall on the right ended up being longer than we had originally envisioned. And we could change just 2 parameters, the length of the wall, and all the code from the robot would then be resulted from our model. So these are not designed by hand. These are again designed by the computer, which makes change management very efficient, because obviously there's digital modeling involved, there's digital connection and building and information modeling, and this digital manufacturing, as in the automation of 3D concrete printing, connects very well with the digitization of the modeling. This is also a good example of a very simple project for concrete printing that results in aesthetically something pleasing just by the complexity of how these things are designed, or the seeming complexity. Here are 3 examples of columns we make. So again, parametrically designed, but these are aesthetic elements. And these are done 2 years ago for the Dutch Design Weeks with the TU in Eindhoven, and are still done with an old technique before we use the accelerant. Now, when we start using the accelerant, this is technology we developed last year, you can see that the material hardens much faster. So no support material is needed. In the previous print, these ones were done with support material like sand or expanded glass to keep it